Well, let me thank everybody for being here this afternoon. The title of this briefing was "Verify No Hazardous Damage," and that's a little bit misleading in that it limits the scope of what we're talking about today. You know, when the CAVE came in and gave us their recommendations, they homed in a lot on NASA needs to go and understand the vehicle and understand the environment. They said a lot about unknown unknowns, about doing the work that's required to understand how we fly. And what you'll see is that the additional tools and procedures and processes that we've put in place and that we'll tell you about today, those are directly applicable to that main thrust of understanding those things. John Murtor said something kind of interesting in the last briefing, which I'm sure you'll remember, and that's that we have analyzed a lot of these problems, the debris transport analysis, the foam shedding, the impact sites, a great deal. He talked about 1 billion computer runs, and we're at almost at a saturation point. And John made the comment that it's time to go fly and get the flight test under our belt so that we understand the vehicle and understand the changes that we have made. And what we're going to tell you about today is the tools and processes and procedures that we have put in place to capture that data. It would be a big shame to go do our flight test work and not capture that data so that we understand what we have for the next flight. And to start that off, I'd like to talk about the launch window a little bit. We've done the launch window definition different for STS-114 and STS-121 than we have done it in the past. The difference is a major focus on lighting. The launch window for those first 2 flights has been constructed based on 2 basic requirements. The first one is for the ground camera operations. NASA looked at what was acceptable lighting for the ground cameras that Christine Boykin is going to talk to you about, and we actually redefined our definition of what daylight is. We had looked at it. It used to be 10 minutes before sunrise. You got the lighting in the sky that was sufficient. We called that daylight. That was mainly for landing operations of the shuttle. We looked at it from a ground camera standpoint, and that was not sufficient. And we did the analysis and redefined what daylight was to have the actual sun limb over the horizon to get proper lighting. And we've assessed that, and that's for the ground cameras what our requirement was. The more difficult launch window constraint from a lighting standpoint, though, was at external tank separation. We wanted really good pictures of the tank. We want to make sure that the improvements that we've made to the different areas of the tank for foam shedding were actually successful. And our first step in that is we went to the ET project, to Sandy Coleman, who briefed you in the last briefing, and asked them to verify that the tank is performing as expected. What do you need to see post-external tank separation? And they gave us a list of requirements. And why don't we go ahead and pull up the very first chart. What we did is we took for different launch times, we simulated in the computer what that lighting would result in on the tank and what you could see. And our launch date, if you remember, is on May 15th. And what this was the 2 days before it, you can see on the May 13th, we did the analysis. We handed this picture on May 13th over to the external tank project, and they looked at it against their requirements and said, no, the protuberance air load or the amount of foam that forms a ramp by the cable tray, you can't see it. And that's an area that we would really like to verify has no shedding from it. So May 13th was thrown out as a possible launch date. We went to May 14th, and you look at it, and you can see the PAL ramp in there, but it's still shadowed somewhat. So we moved to May 15th, and you can see that's where our launch period opening is. We have a really good view of the bipod ramp area. We have a good view of the feed line bellows of the PAL ramp. So what I'm telling you is we defined these requirements. We did the computer simulation, and that's how we came up with our acceptable launch date. Let's go to the next chart. Now for close, it was the exact same thing. June 3rd is our closing date, and if you look at June 4th and June 5th, we start to have shadowing on the bipod, and it just gets worse on the 5th. And so we went through a very specific set of analyses to determine the launch date. Let's go to the next chart. This one I thought was very interesting. this is how good do you do? How good is our computer simulation? And this was the predicted umbilical well camera view for 112, and then what we actually got out of it. And you can see that there's very good correlation between where the shadows were predicted to be and where they actually were. So we have a great degree of confidence in the May 15th through June 3rd launch window that will provide, through the external tank umbilical well cameras, appropriate views to go back and say that, hey, the tank really did perform as we expected it. Okay, to chronologically go through the different tools in flight, we talked about launch window. Christine is going to talk about the cameras, the ground cameras, airborne cameras, on the vehicle cameras. She's going to discuss that. I'd like to go through a few other things before we hand it over to her, though. Another one that hasn't gotten a lot of exposure. We've talked about cameras a lot because we've got the short, medium, and long-range tracking cameras and the ones on the vehicles and things. We haven't talked about radar a lot, though. And back when we did these briefings a year ago, our understanding of what was available to us from a radar standpoint was not very well defined. So the Systems Engineering and Integration Organization pulled together a team from the Department of Defense, industry, academia, and they tackled the radar problem for us very, very hard. And they determined that the radars, the C-band radars we use for tracking from a trajectory standpoint to know where the vehicle is, were not sufficient for a debris shedding tool. But those assets did exist. And NASA went off and purchased 2 X-band radars, and we're borrowing a 30-foot C-band, it's called a coherent radar, from the Navy, and we've poured the concrete. We're waiting for it to cure out in Florida for a 50-foot dish. And let's pull up the next graphic. This is kind of hard to see. Is that a red line going? That's our launch trajectory is the red line, and you can see to the just to the north of the launch site there's a blue dot. That's one radar site where we have a 30-foot dish, C-band dish. To the south, you see another blue dot. That's an X-band radar. And then up along the launch trajectory, there is an SRB recovery ship, the Freedom, that has mounted on it another X-band radar. Let's go to the next chart. And what these show is, if you remember the CABE requirement on cameras, they said you had to have 3 useful views. Well, look what we have here with the radar setup that we have in Florida is the northern radar that we showed you. These are, I believe there's 60-second, 100-second, and 120-second shots of where you'll see the vehicle. So you have from the northern radar the starboard side of the vehicle. From the southern radar, you have the port side of the vehicle. And then the ship-based radar, it's basically coming right over the top of them. So you have a really nice view of anything coming off of the ogive area. Now, we were not greatly experienced in radar. The military folks and the academics gave us a lot of confidence that they could track debris. What we did is a test. We set up the 30-foot C-band and one of the X-band radars and tracked the messenger launch. And the results were unbelievable. And we now have confidence that we can go try this out on 114, try it out on 121 and characterize it and get the same or better debris characterization coming off of the vehicle as we would get with cameras. And obviously what that opens to us is the opportunity to return back to night launch capability. So we're really hoping that the radars, the tests that we do on 114 and 121 will give us that confidence that we can go back to doing the night launch operations. So that's been just an outstanding project for us. Another new technique, and I'm going to go through this a little bit and talk about redundancy. We have this wing leading edge system. I don't have a graphic on it. It's very well written in your press kit on page 42 I was looking at. But in each wing, we have mounted on the spar behind the reinforced carbon-carbon panels accelerometers and temperature sensors. The temperature sensors are just to be able to calibrate what you get out of the accelerometers. And prior to launch, a little microprocessor turns on and it waits for what's called a G switch, which whenever you hit SRB ignition, it turns on the processor. And we'll be taking 20,000 samples per second from each channel of these accelerometers for 10 minutes, which will take us all the way to 2 minutes past external tank separation. And after that 10-minute period, there's a software algorithm in the processor that goes and picks off the peak accelerations, and that can be downloaded by the crew. Well, what does this tell you? This tells you a number of things. One is you'll see events like SRV separation, external tank separation. You'll see how that shock is sent through the vehicle, but you'll also be able to see any impacts that hit on the reinforced carbon-carbon leading edge of the wing. We have mocked that up in the tests that Justin Kerr was showing you when we shot foam at different panels, and we got the results. We're very much looking forward to getting the results on this flight and being able to use that as correlation for anything we might see in the cameras or the radar itself. And Terry's going to show us how that data is integrated into one story, so that we can have corresponding data that shows us that, yes, we had this event and it potentially hit the wing, and here is where. As you can tell, with 20,000 samples per second, it's a huge amount of data. The crew will downlink to us a summary of that data, so we can go look for specific areas of interest, and then at a later time we can download the raw data and see exactly what was happening during that area. Again, this is going to be a test flight for the system. It's a very new system. Although we've used micro accelerometers before, this is a new application for us, and we're very much hoping that this is the future, that this will give us the capability to understand if we've had an impact on the RCC, so that we can pull out our other tools and go use them to characterize any kind of damage that might be there. It also, in my opinion, gives us one of our first real lines of defense against micrometeoroid or orbital debris. In the past, we really haven't had any defense other than if we just happen to stumble upon any kind of damage. But here you have, in one of the more critical areas, the highest heating on the vehicle, where you really don't have a lot of tolerance to orbital debris. You have a capability now to be able to pull out, if you have an accelerometer spike, and be able to go look at that area, so you would have a warning sign of if you got hit by that orbital debris. Now, Christine is going to talk about photos from the umbilical well that we've had in the past that are downlinkable, and I'm not going to take that away from her. But an additional thing that we added on this flight, and we're going to do it on 114 and on 121, and that is a new procedure to photograph the tank from the overhead windows using a digital camera. Now, we've done that in the past. We have waited until all the main propellant system residuals have been dumped, and then we flipped the orbiter around and we've taken pictures if the lighting was acceptable, just to get some data on the tank. But we changed that. The procedure is basically the same, but now we don't wait until the main propellant system, propulsion system propellants have been expelled. We go ahead and flip the orbiter around. We found a new space, a new locker area to put the camera. We put a digital camera so we can downlink the photos. And the difference is that when we flip the orbiter around and take these pictures of the external tank, we'll be about 1,400 feet away from it, whereas in the past we were about 4,300 feet away. So it's about a third the distance that it used to be. And if you saw the pictures from the past, they were not of very high resolution. So we're hoping, of course, our first line of understanding the tank condition is these ET umbilical well pictures that are very close and very high resolution, and we can downlink. But we have this as a backup, and we're going to execute that on both 114 and 121 to give us additional data on the tank. That's a recurrent theme here, is that we want to understand how the tank performs. Now, when we get on orbit, the Flight Day 2 activities are going to be in the OBSS, or the boom, as we call it, the 50-foot extension for the RMS. And that is an outstanding capability to be able to reach virtually any spot on the orbiter. You know, this is one of the unknown unknowns, or an additional tool kind of capability. Those of you that are familiar with the Space Shuttle program, if we had an external tank door stick open, or a problem with any other kind of assessment on the underside of the vehicle, we really had no feasible way to get to the underside. Now with this 50-foot long boom, we have that capability. So it's not just a debris tool, but it also gives you just an access tool if you ever needed it. So I was very excited about that. The boom, of course, is carried on the starboard sill, just like the robotic arm is carried on the port sill. It'll be picked up on flight day 2, and on the end of it, we have the 2 lasers that you've heard a lot about, what we call the Laser Dynamic Range Imager, which is built out of Sandia. I'll call it the LDRI. And then there's a laser camera system that is built by Neptec, which we call the LCS. And there's an intensified television camera on it, which is a really high quality black and white camera on the end of it. So we've got 3 different sensors that can perform 3 different functions. They have different capabilities on the end of this boom. What we simulated in this last mission management team simulation was for what we learned is for different kinds of damage in different places, we understand how each of these tools can be used, and we can apply that understanding to go use the best tool for that particular application. But they're redundant. If for some reason one of the lasers didn't work, we've got another laser. If neither of the lasers worked, you have this black and white television. If the entire end of the boom didn't work and both lasers and the camera were down, well, we have the capability to put a foot restraint on the boom and basically fly a EVA crew member to whatever area we want to go look at. And as part of that redundancy, we developed a new EVA camera that has downlinkable capability. It's a digital camera that's secured, and a flash. We developed a flash that we can use in space, in the vacuum of space as well. So the crew could go and take a picture of any area of interest that we were at. So you kind of see how we build the redundancy for the sensors. You've got 2 lasers, you've got a camera. If those don't work, then you've got the EVA capability with another camera and another flash. If for some reason the boom just didn't work, we couldn't get it out of the latches, or the arm was broken, or was not working properly for whatever reason. Well, what do you do then? Well, early on we took the SAFER, which is the Simplified Aid for EVA Rescue. It's a little jetpack that the crew can use if they float away from the orbiter, if they're not tethered, or float away from station. It's got a little handheld control, which takes up 2 hands. What we did is we modified the suit that the astronauts wear and put a hand controller right here so that they can fly, right here, so that they can fly with one hand and they can hold a camera with another hand, and we manifested a very long tether. So if the boom completely went away and we weren't able to get it out, we've still got redundancy. We've still got the ability to go take a look. And you'll see that as we go through here that you know, radar covers cameras, and once we get on board, the boom has a lot of internal redundancy, and the sensors have a lot of redundancy. And if we can't use the boom, then we've got redundancy to go out. We're going to be able to look. There's absolutely zero doubt in my mind. It's 100% that we're going to be able to assess any sites that we're concerned about. Additionally, on the arm, we made some upgrades, not just to provide power to the sensors that are on the boom, but we also added an additional camera on the arm itself. And it's if I've grappled the boom with my end effector and the boom is out this way, it's a camera that is pointing right down the boom. And the crew asked us to add that after they had done some virtual reality tests with the boom to give them situational awareness. Of course, we're going to have these sensors fairly close to orbiter structure, and you have to be very careful to understand where it is. Let's go ahead and run the video we have here. What you can see is the arm is fully extended out, and the 50-foot boom is down by the side, and this is speeded up. We expect this to take about an hour per wing. The crew is able to look. You can see at the top of the boom there's a little camera that's looking right down the edge of the boom, and that's actually the lower screen on the right of us watching the boom tip, and we're scanning with the LDRI right here. And the plan is on flight day 2 that we have a canned scan that we're going to do to go characterize the underside of the RCC, the front edge of the RCC, and the top all the way along, and and we're going to do that even if we see nothing in the ground cameras, if we see nothing with the wing leading edge system, if we don't have any radar traces, if we think everything was fine, we're still going to go do it. Because, again, this is a test flight, and we want to understand the tools, we want to understand how they work, we want to understand the processes and the procedures, and we want to exercise the data gathering, the data distillation down to the information that we need to get to the management team, the flight control team, and the flight crew. So we're going to go and execute this on flight day 2. Now, this will be a canned survey of the lower side of both wings. We're going to do the nose cap as well, so we'll have characterized all of the reinforced carbon-to-carbon. We'll go think about that, and Terry's going to talk to you in a minute about all of this data that's coming down, all of the camera, all of the radar, all of the wing leading edge, the laser sensors, the camera, all this enormous amount of data, how we're going to crunch that down, and Terry's going to go through how we do all that. Before we get to Christine and Terry, though, there's a couple of additional things. We added another capability, and this is a procedure called the orbiter repair maneuver. And what it is we grapple the station with the shuttle arm and undock while we're grappled and flip very slowly the orbiter around, so that a crew member on the end of the station arm would have access to any point on the underside of the shuttle, which is very effective for repair. It's also very effective if everything else didn't work and we had to go characterize some spot on the vehicle. We have access through that. So again, it's another layer of redundancy. Now, on flight day 3, whenever we are approaching to dock, we have what's called the rendezvous pitch maneuver, and we can show that video now. I think Bill Gerstenmaier showed, he stole my video earlier, but since it's a combined space station, space shuttle procedure, then that's great. There's the 2 crew members, ISS crew members, would be in the service module looking out those windows with redundant cameras, and they are taking pictures of the underside of the vehicle. I heard the question earlier about is roughly 90 seconds, is that sufficient time to photograph all the areas, and Wayne correctly said that it is more than enough time. I was not a believer until they took us over to the virtual reality lab, and we simmed taking the pictures, and you have plenty of time. What we'll do here, though, is we'll characterize all of the lower surface tile and all of the blankets on the upper surface, and determine if there's any problems. Again, it's another data set that Terry is going to get to deal with. Once we get docked, we had talked about micrometeoroid orbital debris. We have learned a lot in the last 2 years about our sensitivity to damage, sensitivity on the lower surface of the RCC, sensitivity on the upper surface, and how those are different, tile damage. And we used to dock and fly with the orbiter lower surface leading, which is a poorer environment from a micrometeoroid standpoint. So we worked with the ISS program to flip the stack around so that we will be actually behind the space station as we are going around the Earth. And we think that'll give us some micrometeoroid orbital debris protection. After we've done that, we've got some things. Steve Polis is going to come and talk about tile repair next. We're going to go out EVA. We're going to test our first 2 lines of defense for repair, and I'll let Steve go ahead and talk about that more. The thing I wanted to get across here, though, was there seemed to be a perception in the community that we're going to do 2 test flights and then we're done, and then we're going to get on with doing ISS assembly. And in my office, we work long-term manifest activities, what we're going to do on flights 5, 6, 7, 8, 9, 10 flights out. And what I want to tell you is that perception is dead wrong, that this vehicle is a test flight vehicle for 28 flights right now, and that we are actively pursuing opportunities to go and do additional tile repair tests, DTOs, on future flights. We're actively working to upgrade sensor packages so that they're They're more capable, but also more user-friendly. As we go along, we're going to continue to evolve. We're going to continue to develop. We're going to take a lot of the redundant things that we have right now and maybe distill them down into more usable packages. We're very comfortable flying with what we have on 114 and 121, but we want to get better. We want to be able to integrate those into the assembly missions that we have coming up. So this is the comment was also made on upgrades. And when we talked about cockpit avionics upgrades, we were never thinking about tile repair or RCC repair or inspection sensors or those kind of things. And that's where our safety upgrades are. And we are actively and very vigorously pursuing those upgrades to have better tile repair, to have better RCC repair, to understand the vehicle better. So if that perception is out there that you think we're going to do 2 test flights and then knock it off and go back to business as usual, that is a misperception. And from an upgrade standpoint, we are spending the money and spending the workforce and spending the time and putting all the emphasis on continuing to improve this vehicle in the long term. Okay.
Good afternoon, and I'm here to talk to you about all the cameras that we're adding to view launch all the way from liftoff all the way through ET separation. For STS-114, we've added cameras on the space shuttle itself. We're upgrading the ground cameras, and we're adding actually 2 aircraft with cameras for 2 flights. Since I have a lot to cover on, I'm going to start first with the shuttle-mounted cameras. They're a subset of the cameras in the Elvis project that I'm the project manager of, and that stands for the Enhanced Launch Vehicle Imaging System. For STS-114, if you show the first graphic, please, the plan is to add 3 new cameras for this flight, 1 on the ET and 1 on each SRV, and they were mentioned earlier. Sandy and Tom told you about the cameras there. Also, we're upgrading 2 of the cameras on the orbiter, and in all cases, we've tried to maximize the use of the existing hardware and systems for a safe implementation. Moving on, I'm going to start first with the ET camera, and as Sandy Coleman mentioned this a little bit earlier, this is the same hardware we used back on STS-112 in October of 2002 for launch. To remind you of that view, we have a short clip of that, just to refresh your memory since it's been a while. And this camera was located up on the top of the tank, and as you see, we get to see the orbiter, the launch pad, and the Kennedy area as we lift off all the way through SRV separation at that time. So this is a nice, unique view that we had. That was the first time we'd flown one of those. The camera for 114 has been moved to a new location to change the view and give us a better location to see the area of interest. It's been moved to the liquid oxygen feedline fairing housing, and the camera has been recased to fit in this new location, but otherwise the hardware is the same. The expected view from this new location is on the next graphic. As you can see, we get a better view of the feed line itself, the bipod attached to the intertank flange area, and the underside of the orbiter. The next graphic shows the configuration of the ET camera, and on the bottom left-hand side, these are the S-band antennas, again the same as used on 112, except this time we've moved both of the antennas to the back side of the tank to keep them from being any debris source to the orbiter itself. The camera is shown on the right-hand side is up in the feedline fairing housing looking back down the tank, and as I mentioned, the camera is in this new casing that's in the little inset so that it would fit up there in that feedline fairing housing. All the data is transmitted to an electronics package which is inside of the intertank itself, and then it's transmitted to the ground using to 4 ground stations and fed live to the imagery labs and the rest of the NASA TV. Additionally, the recordings will be made of the digital signal itself at those ground stations, and then those will be the ones that we primarily use to do our image analysis with, is the digital recordings as opposed to the live feed. Okay, next I'm going to talk about the SRV cameras. And Tom Williams mentioned these cameras, and these are mounted in the forward skirt looking at the adjacent intertank region. They've been flown before, so we just re-implemented those, reactivated those cameras, and we have a clip from the STS-95 footage. And I think it's the same one that Tom showed you. You get to see, as you see the intertank area real close to right where the cameras are. You get a picture of the tank as it goes flying by. And then you watch the opposite SRV as they tumble all the way down to splash down.
I'm glad I don't get to.
I could have cut that one off. We also have a graphic on these just to show you what the closeout looks like. The camera canister and the recording is located in the skirt. As you can see on the right-hand side, it's just a little window that the camera is looking out of to get the intertank right next to where your camera is. This data is also a video camera, but except it's stored on the SRVs themselves. And so we don't get that data back until we've actually towed back the SRBs, and that's approximately 3 days after launch. And then we'll pull the data out of those and transmit those to the labs for analysis. Lastly, on the orbiter cameras, as I mentioned, we've upgraded 2 of those cameras. It's the same set of cameras that we've used in the past for ET separation, except that instead of being film cameras, we've upgraded those to digital cameras. John has already talked to you about that crew handheld. Since we've flown those in the past, it was just a case of telling the crew to use that to do the imagery of the tank. But the umbilical well camera we've updated to digital, so we get really good pictures of the ET surface and the foam that we can downlink to the ground during the mission itself instead of waiting to landing and pulling the data out of the orbiter. These are all COPS items that we've modified. These were modified actually here at JFC by the engineering lab, and they have been modified to withstand the shuttle environment that they're in, so they work all the way through the mission. The umbilical well camera, we also had to modify it to store the images and then transmit them up to the crew cabin so that the crew could downlink those to the ground. And the handheld that John mentioned is just like your own digital camera. We just take the data card out, put it in the laptop, and then downlink those images to the ground. So the ET camera and the SRV cameras have all been mated and closed out and installed for both STS-114 and 121 at this point. And the orbiter umbilical well camera was installed on Sunday and tested, and that works fine. So that's our complement for STS-114. Next, I'm going to talk to you about the cameras on the ground that we've made changes to. We've done a lot of those to upgrade our capability since 107. We've upgraded them, we've relocated some, and we've also added to those capabilities so to give us a better set of video. I have a video that shows you a clip of some of the trackers and the test that was done back in March, on March 24th. Run that. You see they were during this end-to-end test, they set up the cameras. This is bore sighting and making sure that we can actually, that the cameras will work, that they can locate the launch pad, that they can go through the entire planned trajectory and track of the cameras. There's 2 different trackers in this video. The first was one of the long-range trackers on the Navy berm down in Cocoa Beach, and the second one is one of the medium-range trackers on North Beach. And we just full end-to-end tested the system of ground cameras, simulated even traffic, from the launch, so we could get the data back to the lab and in time to support the analysis and data drops that were going to the labs. I'm going to run down through the types and locations of the total ground camera suite, and I believe this is all in the press kit that you were given. We have both film and video cameras, a lot of different types. For the film cameras, and they're the ones that we do our primary analysis with, we have 70mm so-called big sky cameras that capture the whole event. We also have 35mm and 16mm cameras. We have NTSC quality video cameras, and we've upgraded to some high-definition television cameras for this flight. And we're also experimenting with a couple of high-speed digital video cameras just for this one flight to test out that technology. So we have a total of 103 cameras now, and we had 80 for us this one. Oh, I'm sorry. Cool. No problem. I tend to get a little bit fast when I get nervous. So. And I think it's all in the package that you were given, so hopefully I'm just repeating what's in there. We have some 70 millimeter big sky cameras. We have 35 millimeter cameras. We have 16 millimeters. And I'm going to give you numbers of each one here in a minute. And the film cameras are what we do our primary analysis with. We also have some NTSC video cameras. We have some high-def video cameras. And as I mentioned, experimenting with a couple of high-speed digital videos. So that's a total of 103 cameras on the ground for 114. And we had 80 for STS-107. We have the cameras are on two different kind of mounts. One is the tracking mounts, and those are the ones that follow the shuttle through its ascent track. And for the tracking cameras, we've upgraded most of the video cameras that are on those trackers to HDTV instead of the normal video cameras that we had in the past. We've moved some of these tracking sites around to give us better coverage, and we've added 7 new sites for this flight. For the short-range trackers, I have the next slide, please. This shows where the trackers are located. And actually, this graphic also shows you where some of the fixed cameras are. The short-range ones are within the perimeter fence of the launch pads. They cover from liftoff to about 1,200 feet. Each camera site has got 2 35 millimeter film cameras and an HDTV camera on it. There are a total of 3 sites of short-range trackers, and 1 is new for 114. For medium-range trackers, shown on the next graphic, those go from liftoff to about 6,000 feet, and each one of the medium-range sites have got a 35 millimeter camera. They've got video cameras. Can I have the next graphic, please? There you go. Thank you. And also, one of the sites has got a 70 millimeter big sky camera on. We have a total of 6 long-range tracking sites. One of them is new, and one of them has been moved. So essentially 2 new sites for this flight. And then the last tracking type we have is the long-range trackers, and that one's shown on the next slide. And the purpose of those is coverage from acquisition of view. Some of those can pick them up right off the launch pad. Some of them have to wait a little bit to get it. But they go from as soon as they see it all the way through 15 seconds post SRB separation. Each one of those sites has got a 35 millimeter film camera on it, a video camera. All of the NASA-owned ones have been upgraded to HDTV. The ones owned by the 45th Space Wing have remained at NTSC. And 2 of those sites also have one of the 70 millimeter big sky cameras on it. We have a total of 11 long-range sites now. 5 of them are new for this flight. So that's a total of 44 cameras. If you count up all the long-range tracking, or all the tracking cameras, there's 44, and about 8 new sites. Okay, besides the tracking cameras, we also have fixed cameras. These are ones that are just stationary, and the shuttle flies through its field of view. They include pad cameras. There's cameras on the tower. There's some operational TV cameras. Those are located within the pad perimeter and on the towers as well. And we also have some PAO video cameras that we can use. And for example, one of the PAO cameras is on the DAB roof. We have another one at the press site. And if we need to get to those for analysis, we can get a copy of all that data. We've added 2 new fixed site cameras on the launch pad area, and we've upgraded 3 of the OTV cameras that are inside the fence to HDTV for this flight. And we are experimenting with a couple of high-speed digital video cameras. They're going to be located at one of the medium-range sites, but they're just going to be fixed cameras to try and prove out the technology. On the launch pad, we have 32 16 millimeter cameras. 2 are new. The rest have been there for a while. We have 5 35 millimeter cameras, PAO has 6 NTSC video cameras. For OTV, we have a total of 12 video cameras. 3 have been upgraded to HDTV for this flight, and then we have the 4 experimental cameras for a total of 59 fixed cameras. So the last 2 years have seen a lot of changes on our ground camera system. We've added them, we've added additional types, upgraded to HDTV where we could. We've also added a lot of new locations for us to use since 107. Okay, and finally I'm going to talk about for 2 flights, we have the 2 WB-57 aircraft are going to be outfitted with cameras. This project is called the WAVE, which stands for WB-57 Ascent Video Experiment. And we have a video clip on that one showing some of the bench checkout and assembly up in Birmingham, Alabama. This project is a collaboration between the JSC Aircraft Operations Office here, Marshall's HDTV Program Office, and it's all under the leadership of KSC's Intercenter Photo Working Group Chairman. It's a ball turret mounted on the nose of the aircraft, and it was actually tested here at Ellington last week and flight flown to make sure we weren't inducing any environments in the aircraft. The WAVE consists of a ball turret mounted on the nose of the aircraft. Each turret contains an HDTV, a near-infrared camera showing the same optics. It also has a gimbal segment and all the associated electronics. And since the camera has such a big telescope on it, it also flies a standard definition video camera just to help capture the shuttle when it lifts off so we can get oriented and located on the shuttle itself. The cameras are controlled by an operator back in the aircraft. They can either manually control it or put it on auto track of the shuttle itself. And we have 2 aircraft flying in a racetrack type pattern, mirror images of each other, one to the north of the shuttle track and one to the south of the track. They are optimized to be at the point closest to the shuttle, right at SRB separation, flying at about 60,000 feet in altitude. Those cameras on the WAVE are going to image the shuttle from near liftoff to at least SRB separation. We're going to try to get as much past SRB stuff as possible, but since it's the first time we've used these, it's kind of touch and go at this point. So we're going to do the best we can, but at least get through SRB separation, which is our critical debris region. The data on these cameras will be available to the image analysis teams about 8 hours after launch. And also we're going to use these WAVE aircraft for our landing imagery. We're going to add that to it, and film approach and landing of the orbiter for STS-114 and 121. So this is a really exciting new capability that we're testing to hopefully enhance our imagery at and past SRB separation. So in conclusion, for all the cameras, we've taken lots of steps to enhance our imagery. We've augmented and upgraded the ground cameras. We've added cameras to the vehicle itself and continue to do so. We're going to be adding more cameras for starting with STS-115 and flying the 2 cameras on aircraft for 2 flights. And hopefully, if that proves out, we might implement those for further flights. And all of this will provide greater and unique valuable engineering data to us to assess the ascent environment, identify and track debris, and continue the safety loss of the Space Shuttle. And now I'll hand it over to Terry.
John and Christine have both told you about numerous assets that will be in place for STS-114, and John's already alluded to the fact that it's an enormous increase in the amount of data that we'll need to process. So the shuttle program recognized that we would need a plan that would help to ensure that we could get the processing and analysis and integration of that data complete in support of the timely decision making that's required for clearing the shuttle TPS for entry. Okay, the operations integration plan for TPS assessment documents that plan, and it can be divided into 5 logical pieces. The first piece has to do with the processing and analysis of the ascent debris data to identify any potential areas of interest for a focused inspection. The second piece would be the on-orbit surveys that John had talked about. Those surveys would produce additional areas of interest. The third piece would be the processing and analysis of any focused inspection that was required on those areas of interest. And then fourth, we get to for the focused inspection data that was collected for the areas of interest, the detailed damage assessment. And then finally, if detailed damage assessment was performed and had resulted in a repair recommendation, there needs to be a repair assessment. So the first part of that, again, is the processing analysis of the ascent debris data. That includes all of the cameras that Christine talked to you about, the ground-based, the vehicle-based, the airborne-based visual imagery. It also includes the radar imagery that John Shannon talked to you about, and it will include the wing leading edge instrumentation sensor data. Analysis teams at Johnson, Kennedy, and Marshall will do the analysis and screening of the visual imagery. There's a new radar analysis team that will be located at the Kennedy Center to do the screening and analysis of the radar data. And there will be a wing leading edge instrumentation sensor team that will be located in the mission evaluation room here at JSC. When an event is identified by any of these component analysis teams, a verbal report will be made to an imagery integration manager, and that's a new position that we'll have for 114 that will be staffed round the clock in the mission evaluation room. And that event then will be relayed to the other component analysis teams to help them focus any screening and analysis that they are doing in their products. That event will also be relayed to the debris transport analysis team in case a transport analysis is required. In addition, the Imagery Integration Manager will log that event into an integrated debris log, and they will perform an initial assessment as to the relative cooperation amongst the different assets that are reporting. By about 12 hours into the mission, the ascent debris environment from a quick look standpoint will be pretty well complete. And I want to emphasize this is from a quick look standpoint. We haven't gotten any of our engineering films available yet. We have wing leading edge summary data. We might not have any of the raw data. Radar will continue to process for another 12 hours. So this is a quick look, but we do have a good set of data at this time. And the assets at that time, all of the analyst teams will meet and they will perform a threat assessment. So we'll take that integrated debris table and they will together as a team discuss the corroboration of those events so that if an event is reported by both the visual imagery team and the radar imagery teams, that will be recognized as one event. It will have a higher corroboration placed on it, more confidence given to that event, and then the threat as to whether there's potential damage in any areas. The TPS damage assessment teams will then use the results of this integrated debris log to predict damage and to prioritize the review of the imagery data for the on-orbit surveys. As additional events are identified, the debris transport analysis data becomes available, and additional integrated threat assessment meetings will be held, and then the required updates will be made to that integrated debris log. To help us manage this information and this data, we have developed 3 new tools. The first of those tools is the TPS status assessment tool. This is a web-based tool. It's going to be used as a repository for all of the individual analysis teams' formal reports. This will make the data available to the entire community in one location. It will also provide the survey and focused inspection reports as they become available, and the damage assessment reports. It will contain a log of the damage and a graphic that I'll talk about later. We've also developed a ground support timeline that will provide a schedule of the analysis and the reporting as we expect it to occur. And since many of the ground analysis activities are driven by the operations timeline, once a day as the flight plan is updated, we'll update the ground support timeline. The final tool is called Fusion, and this is a tool that will allow us to provide an integrated view of the ascent environment as seen by the visual imagery, the radar imagery, and the wing leading edge sensors, in addition to any debris transport analysis data that we have at the time. I'm going to show you a video of this in a minute. I want to explain it a little bit before we get there. The video is from a simulated ascent in which it had both a radar indication and a wing leading edge instrumentation indication. From those indications, the debris transport analysis is projected to track. We've gone ahead in this simulation and integrated the visual imagery, although within the visual imagery for this event, they haven't identified anything. However, it will help demonstrate the capabilities of the tool. When you see the video, there's going to be a couple of green boxes on the screen, and those are where radar has identified points of origin of the debris. And as we go through the liftoff, you'll see those boxes move as the radar has projected that movement. There'll be some dotted lines on the graphic, and those will indicate the transport analysis where they projected that impact to go. And then also you'll see, as the video runs, the wing leading edge sensor indications of that event. It's important to note, due to the two-dimensional nature of video, the points of origin appear to be on the top of the orbiter when in reality they're behind the orbiter, between it and the stack. And that'll become apparent as in the video as the shuttle rolls through ascent. So I think we're ready for the video. You can see in this video, initially it was showing the model, and now we've overlaid it with the visual imagery. We're running the video at about 3/4 time, and you can see the first event there at 6 seconds occurred, and we have an indication on the port wing of a wing leading edge strike. The second event should be, there it is, 12 seconds. And again, you can see where the radar saw the object move, and also where debris transport projected it. And now that it's rolled, you can see where the point of origin was more likely to have occurred. And our goal is to be able to have that product available for the first MMT meeting on flight day 2. That completes the first phase of the TPS assessment and brings us to the collection, processing, and analysis of the on-orbit survey data. The analysis of the on-orbit survey include the LDRI data that John had talked about of the wing leading edge. We'll have LCS imagery of the nose cap. We're also going to get some CTVC imagery of the forward fuselage from the RMS end effector, digital still imagery of the OMS pods out the aft flight deck, and we'll get the digital still imagery from the ISS of the upper and lower TPS surfaces. All of the survey imagery is screened by imagery inspection teams here at Johnson Space Center, and those teams include both image analysis experts for the specific data source that's being analyzed, in addition to the subsystem experts for the TPS that we're looking at. If we can have graphic 1. This is a sample from the laser dynamic range imager. The survey data is video data that comes down KU real time. It's processed in near real time to correct for hardware-specific distortions and to remove the flicker that's induced by the laser. This sample frame from the simulation shows several areas of interest that were identified by the screening team. Based on this type of screening, the image would then be processed to register, average, and sharpen the image prior to providing the measurement information for consideration as a focused inspection target. The next graphic, please. The second survey I wanted to talk about is the RPM imagery. This is a sample of imagery from ISS using an 800mm lens taken at 7,000 feet. It's an estimated 7,000 feet. Of course, the imagery that we'll obtain from the R-bar is at 600 feet, so we're expecting an order of magnitude better resolution in that imagery. From this imagery, the team will systematically characterize the imagery as either a no concern, a clear violation of the 2D criteria, or questionable violation of the 2D criteria. And based on this characterization, the areas of interest that were questionable violations would be measured first for actual measurements, and those that were clear violations of the 2D criteria would also be measured at this time. The processes for the nose cap, the OMS pod, and the forward fuselage survey screening and analysis are similar to those that were described for the wing leading edge and upper and lower surface TPS. These areas of interest, as they're identified, a verbal report again would be made to the Imagery Integration Manager. If any of these areas hadn't been previously identified as areas of interest by the ascent debris analysis, The Imagery Integration Manager would request that those ascent analyst teams would perform a second review. The Imagery Inspection Team would also post these events to the TPS Status Assessment damage log as they became available. We could capture graphic 3. In the TPS Status Assessment tool, we have a capability to graphically indicate where the damage has occurred, and this is a graphic from the simulation we ran for the MMT simulation. For each of these areas, you can click on one of the damaged locations and you can get specific information relative to the location and the size in 2 dimensions of that area. You can also, from that location, collect all of the detailed inspection reports that would be available. So based on these areas of interest that have been identified both in the ascent debris environment analysis and in addition to the survey data, the damage assessment team will provide a prioritized listing for focused inspections. And that brings us to the focused inspection portion of the Ops Integration Plan. If we go to graphic 3, for either an LDRI intensifier or a laser camera system 3D point cloud, the imagery inspection team will generate a graphic. And this is a sample of a graphic from the MMT sim in which we have some tile damage, and it's a side view graphic. We'll also have top views, and the other side view will be available also. The damage assessment team will then take this 3-dimensional representation and they will run a series of thermal and stress assessment tools to generate the enter as is or repair recommendation. And that enter as is or repair recommendation will be based on positive structural margins of safety in addition to maintaining positive tile integrity margins for tile. The RCC detailed damage assessment uses a little bit different process. They have a tolerance threshold map that was generated pre-flight from the ArcJet testing, and that's how they will generate their enter as is or repair recommendation. For RCC, that recommendation is based on the structural integrity of the carbon system. And for both the RCC and the tile recommendations, those are brought to the admission management team for a risk assessment and final decision. And then finally, the repair assessment recommendation. If a repair had been required, it uses the same tools and the same processes as the damage assessment recommendation. And again, that recommendation would be brought to the MMT for a risk trade assessment. That concludes the operations integration plan from a logical perspective. From a timeline and decision-making perspective, it's really important to understand that the TPS assessment story is one that unfolds over several days of the mission. The shuttle program has put into place a system of early indicators with the quick look, HDTV, the radar data. However, we get our better engineering quality data later. Same with damage assessment. We have the initial surveys on orbit that will tell us where we have potential areas of interest, but it won't be until we gather the focused inspection data that we will know whether there's actually any damage. So it's highly probable that as the story unfolds, that the story will change. It's very likely that what we've identified as a threat on flight day 1 is not the same threat that we'll be evaluating on flight day 3 when we've gone through and finished our on-orbit surveys. So it's really important that the teams remain disciplined enough to wait for and adjust to this new information. And finally, just a couple of words on the readiness of the teams to support this plan. We started developing this plan over a year ago. We took an initial cut at documenting the plan, and then we ran through some paper simulations. We adjusted the plan based on those paper simulations. Each of the component teams, as their tools and facilities became ready, have executed standalone component sims. We've also executed simulations in a little mini integrated environment where we run through all of flight day 1 so that we'd have all of the different assets available and reporting into the flight day 1 process. And we've also supported the mission management team simulations. So we feel that the teams are ready and the process is ready, and we're anxious to support STS-114.
we threw a lot of things at you, and I just want to take 5 minutes here to try and stitch it all together to kind of let you know. This is a tale of 2 flights. This is 2, in my mind, it is 2 separate and distinct flights that we're going to go fly on May 15th. Launch day, we show up with a redesigned tank with the SRBs with good bolt catchers. We've got an orbiter that's been refurbished, and we talked about actuators and wiring and butcher paper and flex hoses and all the different things that we've done to the orbiter. When we launch, we're going to have very specific lighting requirements for all of the ground cameras that we're going to have at the Cape. We've got the vehicle cameras. We're going to track the vehicle with 3 new radars to give us an assessment of the debris. We'll have the 2 airborne cameras suites on the WB-57s. We're going to see SRB separation from the SRB cameras, the external tank cameras, these airborne cameras. We're also going to see external tank separation, which we've never seen before. We'll see it from the perspective of the tank itself. You could kind of see a shadow on 112, but it just kind of hinted at what we're going to get on the next flight. As the tank falls away, we're going to image it with umbilical well cameras, and we set up the lighting criteria to get great views to understand how the tank behaved. We developed our new procedure to be close to the tank when we take pictures out the overhead windows. We're going to downlink the wing leading edge data and be able to lay that into the imagery and radar data that we got. On flight day 2, we'll take the new boom out, take detailed readings with the laser on all of the reinforced carbon-carbon. We've got all kind of backups, which I went over probably too much earlier, but we laid in a number of different sensors and then EVA capabilities to do it. On flight day 3, as we approach ISS, we'll do our pitch around maneuver and take pictures of all the rest of the vehicle at critical damage sizes to understand it. And then, the piece that we didn't talk about with hardware is once all that data is gathered, we have a brand new mission evaluation room that we built in the last year that is just a fantastic facility that allows all of our engineers to show up and have a capability to communicate with other centers and other experts. They go through all of their data processing. They provide that data to a brand new mission management team and a brand new mission management facility that was built specifically to support shuttle only. And that facility has this incredible telecom capability where we bring in other NASA centers. For the sim, we had 5 NASA centers participating, as well as the NASA Engineering and Safety Center, the NESC, the Independent Technical Authority, Safety and Mission Assurance Groups, which these are all new organizations to us that we're going to go fly with, and essentially a new systems engineering and integration organization of which Terry is a part, that has been completely rebuilt from the ground up. On flight day 4, we install the MPLM, which is for the ISS. But then we've got space in the timeline to use the boom to take the data that Terry and her team presented to the mission management team and go look at other areas of interest. And with all the data that we're bringing down, I have a very hard time believing that we're not going to find some areas of interest that we're going to want to go look at. So on flight day 4, we're going to go do that. Flight day 5, you go EVA, and we're going to test a tile repair capability and an RCC repair capability. We're flying 5 different repair capabilities, and Steve Polis and Laura Bailey will go over that with you in the next briefing, and none of which we had before the last flight. If a repair was needed, we developed 4 different ways of getting to a repair site, either off the station arm or the shuttle arm, or putting a crew member on the boom like I described before, or that orbiter rotation maneuver where we can, orbiter repair maneuver where we undock while grappled to the station and go to a place. So we've got 5 repair techniques and 4 different ways of getting there, and I've gone through all the sensors and things. And that's kind of the first flight that we're flying here. It's this inspection, repair if required kind of a flight. And then we get to what the shuttle was built for, and what we really are flying for. It's the transition to that second part of the flight in getting to the ISS assembly and resupply part of the mission. We're going to replace the control moment gyro We're going to install the external stowage platform and LRUs. We're going to do transfer. We're going to take some things that have been cluttering up the station and bring them back home for the ISS program. But you can see the priority of this mission by what we do first. We're going to go inspect the vehicle. We're going to understand the vehicle. We're going to do all the things we need to understand this environment. And then we're going to proceed and we're going to do the different things for our station partners. We touched on it in a couple of the previous briefings on the safe haven or the crew rescue. We've done our homework, I think, is what people were just trying to tell you. Is we've done our homework to understand if we got it wrong, if the external tank redesign did not work, if we damaged the orbiter, or if we had some other kind of problem. We have done our homework to at least understand what the capability is on board the station. And there were questions asked about bringing the crew back. We've done that homework as well. We've designed the recumbent seating. We've redesigned the escape pole. We've done all the things that we can think of to be able to return a crew, although we never want to do that. And it doesn't end with 114. On 121, it is the exact same thing. We're going to have the ground and airborne cameras. We're going to have our radars. We're going to have our boom inspection. We're going to do our rendezvous pitch maneuver. We're going to have the wing leading edge sensors. All those things are being done, but we're going to do even more on 121. We have an EVA that is dedicated just to going out on the boom and understanding the loads that a typical repair maneuver might put on that boom and on the RMS, so we can further characterize our repair capability on that. We're going to take an infrared EVA camera out and go and look at the RCC and how it's heated by the sun and then how it cools. If you have seen the different damage models and things, one of the big criteria, and if it's a catastrophic damage to RCC, is called delaminations in the composite material. If you have delaminations, it allows heat to get in there and erode the surface much more quickly. Well, you can't see delaminations with a laser or a camera, but you can see it through thermography, and so we're developing this camera that we think we can use, and we're going to go test that on 121. We're also going to test 2 additional repair out of those 5 capabilities on 121. And in those, I think these 2 flights, we put this, I don't know the page count now, Terry, but it's like 305-page flight test plan of all the things we would like to check off from the first 2 flights so that we can continue to fly in a really safe and robust manner. In my goal in this summary is to let you know that we are doing a tremendous amount on 114 and 121, and we're going to continue to do a tremendous amount to understand the environment and understand the vehicle, and we're going to get better and better as we go. And I hope that helped stitch together all the various different pieces that we've kind of been throwing at you today. And ready for questions, Kyle.
I can. Let's start with Bill on the front row, and then Stefano over here is number 2.
Sorry, CBS. Can one of you walk me through the first couple of days of the mission and tell me what the media is going to see and when? I realize there are some variables there, and I see John Shannon smiling, but as I covered your recent snow, I was struck by how long it took for all the products to come in. I think some of us are expecting, well, it's video, we'll see it right away stuff. Obviously, that's not true. Can you walk us through what's available to the public when, and when you get to the point where you have enough to make a definitive assessment of the condition of the vehicle?
I'll start with what Imagery will have available when. A lot of the enhancements that have been put in place are to give us that quick look video imagery that on the first day. The HDTV views will be transported within the first 8 hours. We should have a considerable number of the short, medium, and long-range trackers views at the image analysis facilities, and we do not intend to hold that video. We intend to make it available to the public immediately. Relative to when assessments can be made, the plan, again, it's an unfolding plan, so we really want to make sure that we wait for the right level of data to make the right assessments. The first assessment is the asset debris assessment, and that data will be for relative to the TPS inspection and areas of interest. We'll have that data pretty much in the first 24 hours. The second piece of it is the on-orbit surveys. Those occur on flight day 2 and flight day 3. We expect to then, at that point, within 6 hours, in the middle of flight night 3, to have a focused inspection prioritized list for the flight day 4 focused inspection operations. A lot of what we're doing is very tightly coupled with the operations plan, and that's when we will be providing the data. The plan is then outlined to support what the ops team has developed as an as-planned repair timeline, and based on that, the decision for a repair comes on flight day 6. That allows about 24 hours of assessment once we have the dimensional data for the damage assessment team. That's for a nominal as-planned timeline, and I think Mr. Hill later tomorrow will be speaking to you more about the options we have to change that timeline.
Stefan Pledan for Popular Mechanics. What have you done or are you doing in order to prevent a repeat of what happened during the 107 launch when you had the, I believe it was the Cocoa Beach tracker that was slightly out of focus and you missed the best view of the launch? And also, if I can squeeze one in, is what altitude of the WB-57 going to be flying?
To answer your first question, dealing with making sure we resolve the issues with some of the things, the camera that was out of focus was actually an Air Force asset that we used, and we have made some changes to our procedures so that each camera has to be checked, and the Intercenter Federal Working Group Chairman notified before launch on the condition of each and every camera. With 107, we just had it essentially defined as does this group of cameras work? So there wasn't a lot of individual camera feedback. So we've changed that so that we get a report pre-flight on every single camera, and it will be up to the Intercenter Federal Working Group Chair to either say we have to hold because we need to fix this camera, or we've got other cameras that are working that will cover it, and so we're good to go with that one. And I missed the question on the WB-57.
What altitude are they going to be flying?
Altitude, I believe our target altitude right around the SRV set time is 60,000 feet.
Todd Halverson of Florida State for John Shannon. You mentioned modifications to the pole system, and I was wondering if you could elaborate on what modifications have been made to the escape system and procedures and whatnot, and what challenges you see would be involved with getting an entire shuttle crew plus a rescue crew out if that indeed became necessary.
Thanks, Todd. There's really two areas of concern. Let me start with what modifications were made on the escape pole. When you crank it out and it goes out the blown hatch, you have a little ring that you attach to that will pull your parachute out. The very simple mod that we did is we added more rings so we could support the 11 crew members. There was a great deal of concern that when we started the bailout, whether we would be able to get all the crew members out at sufficient altitude to have their parachute open. And we ran some tests over in Building 9, having crews do it, and even getting out of the recumbent seats, and we showed that was something that we were able to do. What would I be worried about? Of course, the biggest concern is that you've had folks that have been in zero-G for an extended period of time, and they have the neurovestibular effects. You've got 4 folks to help them, and it's very hard to predict how that would affect any kind of a bailout. But the case, while we have addressed it, because I think we have really tried hard to have a lot of diligence in all of our different plans, whether they be fifth order backup plans, is that we had to invoke safe haven. We had to send a rescue flight up. It got up there and was able to get the crew, and as we're coming back home, we had some additional problem that caused us to have to bail out. But like I said, we've made the modifications, and we've run the test to show that would be something that we could do. And it falls along the lines of we tried really hard here, because the seats that we put in for recumbent seating there in what's called the ditch area, which is where the internal airlock used to be, and we had a big debate on did they have to meet our 20G crash loads because it's a contingency kind of case, and I was actually against that because I said, well, it's a contingency and it's going to be hard to do and it's going to cost some extra money. And the Orbiter project said, no, we need to meet our certification even though it's a contingency case. And they did it, and they designed it to a 20G crash load. So even though it is a big a contingency case we don't want to get into, we have tried to treat it and treat STS-300 like another flight and do all of the things we would do to give ourselves every opportunity to ensure crew safety and crew health.
Okay, let's see. Next three is Seth, and then Mike, and then Marcia.
Seth Lorenstein, Night Rider. John, just a simple thing here in terms of the window after June 3rd because of lighting for the cameras. Obviously, you've got orbital dynamics meeting up with space station. Mm-hmm. If you're just looking at the window because of lighting dynamics, one, how long is that? And then two, after June 3rd, when does that come along with the orbital dynamics meeting in ISS? So in other words, if you don't make it by June 3rd, when's the next window open up and how long does it go for?
The next window would start, it looks like now July 13th. We were advertising July 12th, and we just got a new state vector from the ISS, and I think we're going to end up saying July 13th, although we have some of our normal processes to go through. It's another 20-day window, just like the May 15 through June 3rd is, that meets all those criteria. I had presented at a Spaceflight Leadership Council that the window closes on June 3rd, and I showed you why on that the external tank umbilical photography. It turns out that we would have about 4 additional days if we accepted that the overhead camera pictures were acceptable, because the lighting gets better as you go a little bit later for those overhead pictures. And we could add 4 days to the launch window, but the senior management took a look at that and said, we really want the high fidelity pictures from the external tank umbilical well, and that's why we stuck to the close of the window being June the 3rd. And it's, we'd like to make the May-June window and the July window, because it's 2 good ones. It gets pretty skinny down in September for meeting all of our lit constraints. Right now it's about September 8th through September 14th, I think we met our lighting constraints.
Mike?
Mike Cavish with the Orlando Sentinel for John Shannon. Give us a few details, if you would, about the on-orbit imagery that's going to come from national intelligence assets. There was a memorandum of understanding. It was a result of the CAVE's recommendations. Is that going to be every mission from here on out? When is that going to come? What sort of views are you looking for? Tell us as much detail as you can about that, including the source of the pictures. Is it going to come from Hawaii or New Mexico or on orbit?
NASA's intent is to use all the resources available to us for every shuttle flight from here on out, and that's all I'm going to talk about on that subject.
Marcia and then Tracy.
Marcia, Associated Press for John. We were talking about the slow sweep of the inspection boom. Do you have any idea of how slowly it is going to move, how many inches per second or fractions of an inch? And is your intent to use that boom to inspect every square inch of RCC on the entire vehicle?
The first one is speed. The last time we talked this, and we're still using data from engineering units, and we're trying to understand, was 1 meter per minute was the scan rate on the underside. Steve Polis, when he comes, will be able to tell you that the damage criteria for the lower and the very leading edge of the RCC is very small. But on the top side of the RCC, it's very large. It's just like a 1-inch kind of hole. And we had a debate on whether we needed to scan that with the laser if all you're looking for is a 1-inch hole, and I can pick that up from the Rendezvous pitch maneuver. So it was 1 meter per minute the last time we talked this, about 3 hours total for the entire both wings. We're going to use the LDRI for the wing. We're going to use the laser camera system for the nose cap. There is one area of RCC that protects the forward attachment. We were having a debate on whether that could, it's not edge on to any debris. If any debris hit it, it would be a very glancing blow, which won't damage the RCC. So we had a debate, and I'm not real sure if we resolved whether we really want to take the time to go look at it or not. I have a feeling we probably will, the way this flight's been laid out. Terry, do we have any updates on scan rates or anything from the last time we talked?
No, I think you've pretty well covered what my understanding of it is. Relative to the analysis of that for the wing leading edge, we expect the analysis to run up to 18 hours from the start of the processing for the screening, and then of course any enhancements that need to be made for measurement to take it to that next level of quality take about 2 hours per image to process out three-dimensional data. There's four workstations available for LDRI to do that processing. So we're thinking 18 hours start to finish for that job from an analysis perspective.
And let's see, Marcia, the way it works is we've taken we've set requirements. The program set requirements for what damage we want to be able to go identify. And then the engineering group has determined what the laser capability is, and we hand that over to the ops team, and they can tell you exactly what trajectories they have programmed in and what the sweep rate is along the wing. So when you talk to Paul Hill on Thursday morning, he can answer that for you.
Tracy Watson, USA Today. I think it's for Terry Murphy. Last time we were all here at JSC, we were told that LDRI would, in most cases, detect the smallest critical damage to RCC, which I think is 0.02 inches. And I'm wondering, under what conditions would you not be able to see critical damage on RCC with your sensor?
Yeah, I think John has already alluded to this, but the sensors are continuing to go through verification and validation, and what they're learning is that the way that you operate the sensors will affect the amount of capability you get out of the sensor. So what we've done is we will optimize for the damage criteria, which is also not constant across the week. It varies. So we will use the sensors in a method to optimize for the damage that we're looking for. The engineering teams feel highly confident now, based on their verification testing, that in all areas we will be able to see the critical damage that we need to.
Okay. I was just going to say that Steve Polis is coming in to do the next briefing, and he owns that system, and I think he can give you additional data on. If you get Steve started, he can tell you a lot about different lighting conditions and different laser capabilities, and I think he can give you a lot of data there. So save that one. Sorry, Eric.
Irene Foster, Reuters. I had 2 questions. The first is, do you have some kind of updated estimate on how much these imaging assets are costing, including the WB-57 flights, the radars, the equipment, and so forth? And the other one is, I understand that every game will be of interest just on a test of the equipment and the procedures, but how far along in this 13, 14-day mission do you think it will be before if everything goes as planned, before you feel that there is not any significant tile damage?
No. On the cost question, we'll have to get you that data, because that is a really complex question. And as we've gone through all the different hardware pieces, we can add that up and tell you where we are on it. From a schedule standpoint, it's Terry's team that's going to be able to decide that, so I'll let her go ahead and answer that.
Yeah, again, what we've done is we have a ground support timeline that schedules that will show where we expect the analysis to occur for each of the assets, and of course that's tied to the operations timeline. Specifically, again, from a quick look asset perspective, we expect to bring that information to the MMT on the first, slightly 2 MMT, the first MMT of the mission. The second MMT of the mission is where we'll bring in the survey data. The third MMT of the mission will be the focus inspection data, and then it will be flight day 6 before we get to the damage assessment.
I'm sorry. Go ahead.
So are you saying roughly it'll be about a week into the mission before all the data is kind of churned through, and at that point, whether there's damage would be known or not?
The damage decision comes at about 5 day 6. Yes, each of the different assets will finish at different time frames. So radar, they've completed their analysis within about 24 hours. The quick look of the visual imagery, about 12 hours, that will then get the film data at 24 hours for the first look at it. There's a second set of film that comes at 48 hours. Some of the recorded data on the SRBs, of course, we won't get until SRB recovery. We get ET digital downlink data available in real time, but the higher quality digital data isn't available until 24 hours. So each of the different assets, as the story comes together, have very different timing.
Let me get Jim, and then Horst, do you still have a question? Okay, we'll get Jim, Horst, and then we'll come back over here.
Yeah. Jim Obert at NBC. John, we remember that one of the most interesting detections during the Columbia flight were the radar tracks of the object coming up on Flight Gate 2 that had some critical data about being a piece of RCC panel. Do you have any further attention you want to pay to objects departing from the orbiter early in the flight, either with the radar ground track or with perhaps even television observation from on board the orbiter?
Yeah, Jim, I have a really high level of confidence that if we have any damage on the vehicle, we're going to be able to understand it and image it either through the Flight Day 2 inspections with the boom or the Flight Day 3 rotational pitch maneuver. In addition, that we're using all the assets available to us. So I have that high degree of confidence that we're going to be able to understand. I got to tell you, I'll show you how the breakdown is. I really feel like based on the ground cameras, airborne cameras, on the vehicle cameras, the radar, we're going to understand if something came off the stack. Through our umbilical well cameras, we're going to understand where it came off the external tank. We're going to have our transport analysis that Terry showed you a little bit of to show where it hit. We're going to be able to a great degree, characterize any damage that is out of that hit. We'll be able to take measurements of it. We'll know exactly where it is. And then the second part, though, you're going to have to hear what Steve Polis says in the next briefing, because that's when it gets really interesting. That's when it's, because there are so many different heating rates on different parts of the vehicle. One damage that might be catastrophic in one spot will not be catastrophic in another spot. And it's a very interesting story on the analysis tools that they put together to, once they get that data that Terry has talked about of, here is damage, here's where it came from, here's what it was, here's where it hit and what it did. Then taking that and putting it in the analysis tools and determining if that is something that needs to be repaired or not, and then how we would go about and do the repair. So the big piece that we didn't cover in this briefing is that analysis once we characterize any kind of damage. We're going to know if something came off. We're going to know if the vehicle's damaged. I have zero doubt about that. Nothing's going to get by us. But what do you do about it after that point? And that's going to be the subject of the next briefing.
Horst and then Peter.
Horst Rademacher, Frankfurter Allgemeine Zeitung. I'm still a little bit confused about the number of cameras, so it's a question for Christine Boykin. You mentioned 103 ground cameras, 44 cameras in the long-range tracking system, 4 cameras on board, or 2 cameras on board each of the WB-57s. So how many cameras are there in total to look at STS-114 on SM?
We do a little bit of quick math here.
107. Is that right, or 107? Is that our magic 107?
107 is part of it. There's about 112 cameras that we'll be looking at.
Thank you.
Let's see, we'll get Peter, and then while you're over there, you can get Dan right behind him.
CBS News Radio, and this question is for you, Mr. Shannon. It's a boom question. I'm curious, how long would it take to attach the foothold to the boom if they had to use it for EVA? And do they have to remove any of the imaging equipment from the end of the boom in order to do that EVA? Or would that still remain attached, and would we have that kind of bird's eye view?
It would remain attached, and it's a very simple procedure to attach a portable foot restraint to the end of the boom. That is not difficult at all. We had some concerns at one point about motion, flying around a person on the end of this 50-foot long, very rigid stick, and we've done the analysis where we're feeling very confident about that. On 121, we're actually going to go do that. We're going to put a EVA astronaut in a foot restraint on the end of the boom and go to different arm positions and try to get it to move. Then we're going to put a second astronaut up there in case we had to do a repair and they had to hand off tools to have the most highly loaded case that we could have. We're building special equipment to put on the interface between the arm and the boom so that we can understand exactly what loads are imparted back into the system. So by the end of the second flight, we're going to have that problem completely licked, and then we're going to have a really nice tool because we're going to have access to all areas of the orbiter, which is something that we have really wanted for a while.
Go ahead, Dan. Right there. No, let's get Dan first, and then we'll get John. Dan Billow, WESH-TV. Kind of a two-part question here. Can the radar imagery that was gathered during the Messenger launch last summer be released to the news media and public here at JSC this week? And the second part is, what are the launch commit criteria for all these new cameras that you told us about? Are there, if they break down, is there some launch permit criteria that says you can't go, or you have to fix them?
I'll take the first part, and Christine can tell you about the second part. The radar imagery, I will check on. We had made an agreement with the Messenger folks that we were just taking the data for our own data evaluation purposes, and we're not making any assessment of their launch vehicle, and we will have to get it cleared that it's okay to release, and we will do that. We will try to do that. And Christine, for LCC?
For LCC and the true sense of the word, as we in the Shuttle program office deal with it, we only have one LCC for ground cameras, and that's for the power for some of the remotely operated cameras, because the LCCs are the ones that run through really close into launch count. So that since we have the power system turns on a bunch of these cameras remotely, there's two of them. We need one of two to be running, so that's the only true LCC in the shuttle world that we have. We do have rules on weather constraints. The cloud decks, the ones that we have already in place, we reviewed, looked at, and made sure those were consistent for the ground camera operations. And for if an individual camera drops out, that data is provided, as I said, to the Intercenter Federal Working Group Manager, and he briefs the mission management team, giving them the complement of the remaining cameras that exist, was that a unique view or not, and that he makes that call, recommendation to the mission management team. But otherwise, we don't worry about, we don't want to have LCTs going really close into the launch count in case we lose a camera, because shutting down is a lot more catastrophic and risky than just not having one particular camera view. For the cameras on the vehicle itself that I'm in charge of, I don't have any LCCs because I only have one that is actually running and feeding data back to the ground pre-flight. Everything else is turned on during the flight.
Okay, let's go get John and then Kelly.
Mark Kirkman, Interspace News. This question's for John. No problem. Actually, it's a two-part question about Windows, and the KSC folks told me to ask you with regard to launch attempts on the pad. It's my understanding you're going to be, if you want consecutive attempts, you would have to trade a Flight Day 3 for Flight Day 4 rendezvous, and my question is, how important is preserving Flight Day 3 rendezvous capability? The second window question is with regard to the RPM maneuver. The cue card says for the crew to wait for a window open. I want to know what the duration of that window is and what what drives that window? Is it strictly lighting? Is it orbital mechanic effects? So forth.
Well, those are two really separate questions. The first one is how important is Flight Day 3 to us? This mission does not have the typical +1 cryo extension day that we would normally use for a Flight Day 4 rendezvous. So we have set this mission up to require Flight Day 3 rendezvous only, and we will not at this point launch into a Flight Day 4 opportunity. That's different from in the past, but we have a significant amount of data we want to gather. The rotational pitch maneuver happens on Flight Day 3, and we have it's a fairly busy timeline. So without that +1 day, we would not do that. The second one was on rotational pitch maneuver. The way we set up the rendezvous, we will set it up so that the lighting, the timing works out that they hit the point directly below the station. It's what we call the R bar, but where they would execute the rotational pitch maneuver at 600 feet. The lighting will be such that they will have, it'll just be set up from an orbital mechanics standpoint that they can do that. And that's all very consistent with our normal rendezvous practices. That's how we set up lighting for docking constraints and things like that. So the truth is that if lighting was not good, or if something happened, or if throw any hypothetical out there you want, you can sit out on the R bar directly below the station for an extended period of time until you're happy with the lighting or whatever else you've gotten squared away. That's one point where you can sit on a rendezvous. The other one is when you're up on the V bar pressing into dock. You can sit there for a long time. From an orbital mechanics standpoint, it's not a big deal. You don't want to do that because your timeline is really pretty tightly choreographed on rendezvous and docking day. So if you're sitting there waiting for something to get better, it just pushes the end of the day later, and you keep the crew up on a fairly busy day. So we prefer not to do that. That's why we set it up a priori.
I have time for two more questions. We'll get Kelly, and I know this gentleman has had a question for a while, so those are the last two.
Kelly Young with New Scientist for Christine. I believe you said the WB-57 was also going to be doing landing imagery, and I wanted to know how far out you expect to see the orbiter, and what's the purpose of this?
I don't have the data on exactly how far out. I know it's going to be approach, part, and landing, so I think it's fairly close to wherever the landing site is, but I can get that information from the folks who really run that operation.
Okay, this will be the last question.
John Kelly, Florida Today. For John Shannon, I just wanted to understand, there's some additional things in here that you're doing, and I'm wondering, are there some additional risk acceptance things you have to do for some of these inspections? I mean, you're flying a 50-foot rigid boom out there, very close prox ops to your wing. You're talking about on the second flight putting somebody on the end of that. A couple of pretty interesting flight maneuvers by Eileen just after dropping the tank and then at the station. I guess I just wonder, is some added risk here that you have to take in order to accomplish these tasks?
It is consistent with the way we always do business. That was a great concern to us. Let's take the examples that you threw out there, which are probably the best ones. Is you've got this long, rigid boom on the end of your arm, and you're taking a look at the most fragile piece of the vehicle. So that that makes sense that you'd be worried about that. That's one of the reasons we added that RMS side view camera. After we did the virtual reality sims, we realized the crew does not have enough situational awareness in this to really make sure that they understand exactly where it is and be able to control it. So we have put together additional hazard reports for those kind of operations, and feel like we understand and feel like the crew is trained and that they're going to be able to execute. It takes 3 crew members to do it, so it is a fairly intensive task, and I feel very confident that they can do it very safely. The other one was the pitch around for after you separate from the tank, and We looked at that, and again, we simulated it. Eileen will tell you she's done that maneuver quite a number of times. Orbital mechanics-wise, you're separating from the tank, and there's really not a lot, you'd have to expend some propellant to try and get back to the tank, so it's safe. Where that one is a little bit painful is in propellant, where we normally dump the residual propellants out the engine belly, and you got some positive velocity out of it. Now we're flipping around, and it's actually going to be negative, and that just means there's more gas that we're going to have to use to get up to the altitude of the space station. But it's a good expenditure, at least for the first couple of flights, because the downlinkable umbilical well camera is new. And we wanted a backup. And as you heard as I went through, we got backups on backups on backups to get this information, because we really want this information on the first couple of flights. So we have, to answer your question more specifically, we've gone through and done the hazard analysis. We've gone through and really put a lot of focus on training of the crew, and we feel very confident, just as we do with the other aspects of the flight, that we have it well in hand.
Okay, that's all the time we have for this briefing. As soon as we can, we'll get turned around for the next briefing.
Okay, good morning. I wanted to start off with sort of a debris 101 discussion, because understanding how the debris is a threat to the vehicle is the key to understanding our strategy for managing the risk. So when we're up and flying together in configuration, all the vehicles flying at the same speed. We're going to sort of work with basics. It's all flying at the same speed. When debris comes off, okay, it's flying at the speed of the vehicle in the same direction. But then it gets out into the environment, and if I use this, I believe this is a divot coming off the tank, it gets out into the environment and it decelerates rapidly. And it's really amazing the physics that are involved in here, because we normally don't live with the physics that happen at 3 times the speed of sound, so it's hard to really appreciate what's going on. But what happens is that a piece of debris, maybe 3 or 4 inches in size, a piece of foam, for example, will decelerate from going 4 times the speed of sound to essentially stop dead in the air in less than 1/4 of a second. And in terms of G's of deceleration, or equivalent to what 1 G is gravity is felt on Earth, in a fighter plane you might turn 9 G's. The kind of deceleration that this debris goes through is an equivalent of thousands of G's of deceleration. Now what's interesting is the debris hangs together because the pressure, air pressure on the debris is all the same, so that it tends to hold the debris sources together, they hang together. And so when the debris comes off, it basically stops in the air. It's still free falling, but it goes in less than 1/4 of a second from going at 4 times the speed of sound perhaps to basically stop. And then the vehicle, which is still going 3 or 4 times the speed of sound, hits it coming up. So that's what makes the debris a threat to us, the degree to which the debris decelerates in the air. Now, the deceleration of the debris in the air is a function of a couple of different factors, one of which is the density of the air. Okay, and of course the density goes down as we go up higher in altitude. Another is the surface area of the debris. So we use those 2 factors in controlling the debris threat and managing the debris threat. Of course, the velocity that the vehicle is going is increasing with altitude as we move up, and so what happens is there's sort of a region of maximum threat when the density of the air is enough to really slow things down, but the vehicle is traveling at a high enough velocity to really cause a large impact closing velocity. And as you go up in altitude, the debris threat goes away. At the time we do SRV separation at about 2 minutes into flight at about 4 times the speed of sound, there's essentially no atmosphere left. And so the debris that comes off after SRV separation really isn't a threat, because when it comes off, it's traveling in a vacuum, and it just sort of travels along with the vehicle for a while and slowly moves away from the vehicle. So our real debris threat region is a time from a little bit after we're clear of the tower until about 2 minutes into flight. So it's a very limited window, and we really work to understand the debris sources that can happen inside that limited window of flight. If we could go to the first chart, given that those are the parameters that control the debris, what we try to do is use aerodynamic theory to model what's going on with the debris. Now, on the left shows you what we were doing before 107, and you can see there's a small number of colored streaks coming from a part of the top part of the tank in the left part of the picture. And those were the kinds of debris trajectories we would have run prior to the accident for a source of debris. And in the orbiter in the upper part of the picture, you see a little bit of colored area, and that's where we would have predicted there would have been debris impacts. After 107, we had a big independent peer review, and we brought in experts from all the NASA centers, Langley, Ames, Marshall, Johnson. We brought in people from Sandia Labs, from Aerospace Corporation, from our industrial contractors, and from academia. Texas A&M was involved. And we also brought in place a bunch of retired NASA personnel with a lot of experience in the original development of the shuttle. And our aerodynamics team at JSC, working with the these experts, really came to the conclusion that this problem is very sensitive to the initial conditions of debris. And because before the accident we had just observed individual pieces of debris and we were trying to track and make sure we understood what those trajectories were, we'd been focused on generating a set of initial conditions for the simulation that would closely match what we had seen in flight. And that colored our understanding of the debris threat. When we went after the accident, what we did was we started dispersing the initial conditions. And what that means is instead of the debris starting off with one velocity in one direction, we started flying it off in all sorts of different directions and all sorts of different velocities. And on the right-hand side of that slide, it shows what our current debris methodology does. And what you can see is instead of a few number of traces, we have a large number of particle traces. And instead of covering a small part of the orbiter structure, it covers a much larger part of the orbiter structure. And the color is basically proportional to the velocity of impact. And what you see is that we have lower velocity impacts up front and much higher velocity impacts as you move back towards the aft of the vehicle. And so that really did a lot to improve our understanding of the problem from mathematical cases. And to kind of give you an idea about how much work was involved in that, we have 16 major debris cases we run. We've got about 155 identified sources of debris during ascent, but they break down into approximately 20 classes. About 16 of them we run in this simulation. And we run about 10 million cases of releasing debris into the flow field for each one of these cases in order to cover all of the initial conditions, all of the locations the debris can come from, the range of possible velocities that could come off, the direction that it could possibly fly. So in our basic analysis set, we have about 160 million cases we run. And basically, we have done this 4 or 5 times. I was talking to one of our experts in the field today, and he said he knew of some cases that he had run as many as 12 different times, each with different initial conditions trying to determine the sensitivity of the problem. So we've run way over 1 billion cases of understanding debris simulations, over 1 billion cases where we have in the computer released debris and looked at where it could go and what the impact conditions would be. We've done that with 4 different models, okay, so that we have 4 different solutions to the problem. 3 of them use the same underlying flow field that we've determined from computational fluid dynamics. One of the solutions has a completely separate approach to the computational fluid dynamics, and it's a whole different kind of modeling approach. All 4 of those modeling approaches are producing the same results, and they're remarkably in agreement. So we have a good feeling that we've got a handle around the modeling, and we've encompassed the range of conditions that we could potentially see against in flight. We've basically been keeping all of the supercomputers in NASA busy working this problem for the last 1.5 years. And in fact, the new supercomputer that was just installed at Ames Research Center, the Columbia project, is the world's largest, fastest supercomputer, and we were the first people running on it, and from the first day it became operational, we've been running cases on it every day. And we're just finishing that work up. We're going to be reporting out all our results in the debris verification review this week. And the concern about this is it's all modeling. And the reason we have to model is because spaceflight is a unique kind of issue. If this was a commercial aircraft or a military aircraft, the proper procedure would be to go out and fly. You'd identify the critical conditions, and you'd get the aircraft, and you'd go out and you'd go fly it at that speed, at that altitude, with that configuration of fuel, gear down, gear up, flaps down, flaps up, weapons on, weapons off. And you'd fly all those conditions to understand and build a complete certification database. But we don't have that option. In spaceflight, when you launch, you have to go all the way the first time. So we don't have the option of multiple repeated exposures to the flight environment to gain the data in order to understand whether our models are correct or not. So instead, what we've had to do is go through a series of validation techniques. Now, each of those are limited in terms of their capability, but they tell us a lot about how well the models are working. So if we could go to the next slide, please. The first thing is to understand how this works. It all depends on the underlying flow field and pressure distribution around the vehicle. And in order to understand that, we have three sources of information for the model. What we compute in the computational fluid dynamics, and the graphic on the left shows a computational fluid dynamics solution of the entire shuttle. Now, 20 years ago, CFD was at the place where it was just beginning to be able to attack total vehicle problems. And here we have got the entire trajectory in the vehicle's model. So this is, we're really fortunate that the CFD tools have really evolved over the last 2 decades. The second is flight data. On the initial flights of the shuttle, we flew quite a bit of instrumentation, which enabled us to understand what the pressure and distribution and flow field was. And the third is wind tunnel testing. And we've conducted the most extensive wind tunnel test campaign that the shuttle program had run since the early 80s. And if you go out into the hallway, you can see the 3% model that we ran in the wind tunnel at the Arnold Engineering Development Center in Tullahoma with the Air Force, and at the Ames Research Center tunnel. The model was built by the technicians at the Ames Research Center, and I really encourage you to go out and look at that model. It is an incredible piece of craftsmanship. And in particular, the detail that was put in place around the bipods, the feed lines, all of the aspects of the external tank were really truly unique. So we have run that work, and we have been able to show that our computational fluid dynamics, our flight data, and our wind tunnel data all line up with each other. So we feel really good that we've got the basic underlying flow field done properly. The next chart. Then there are a lot of assumptions that go in the model, and we've done a variety of tests in order to understand that. At the Marshall Space Flight Center and at Michoud at the tank facility, they've been doing quite a bit of tests, number of tests, trying to understand how divots come off the tank for foam, and we've been doing equivalent tests for ice at Stennis and at Marshall Space Flight Center. And so we need to understand how debris comes off, what velocity it comes off, what the size is, what the shape is. So we did a number of ground tests in all of the element projects to go deal with that. And then on foam in particular, we went and we flew foam panels up on an F-15 up along the shuttle trajectory all the way from basically the ground up to Mach 2 and 50,000 feet, following the shuttle trajectory, ejecting foam divots to try to make sure we really understood the aerodynamics of the divots. And then we've done a lot of analysis of the zones of sensitive impact, and Dr. Kerr is going to talk to you about all the testing we've done to try to understand that. Next chart. Then another thing we've done is we've tried to correlate trends in observed damage that we see in the shuttle's thermal protection system post-landing with what the models predict. And on the left you see on STS-114 a debris map. This was on the shuttle, on the orbiter, the regions of the tile that we showed impacts in, what the little black dots are, after we had a loss of cork off of the solid rocket booster. And what you see on the right, although it's a mirror image, is the simulated distribution. And what you can see is there's really a pretty good correlation between what the model says, where the debris should have gone and where we should have had impact, and where we actually observed the impact conditions post-landing on the vehicle. In the next chart, the other thing we try to do is take specific debris events where we observe the piece of debris in the flow field, and we try to model and replicate that. And on the left is a simulation that the Ames Research Center community did of the STS-114 debris coming off the bipod, And that is a CFD solution of both the debris and a CFD solution of the vehicle flying combined in unsteady flow. It's a very sophisticated model. And then we use that to cross-check against simpler models that we use. And then we also do quite a bit of time understanding the debris aerodynamics themselves, because they can do a lot to determine the velocity and where the items go. So at that point, I think we've got some video to show you of the kinds of testing we've been doing. This is the test we ran out at the Dryden Flight Research Center with an F-15. The particular test we're going to show you here in this particular clip is with using what we call blue foam, or typical foam used in house insulation. We used this during the initial development testing, and we used this to prove the concept. And what we did was we had panels of foam where we inject a small amount of air behind it in order to get debris liberated off of the foam. After we developed the technique, we then went ahead and did that with actually with ET foam provided by the ET project. I think we've got a video of that also. Okay. This is actually in a wind tunnel. We did the same problem in a wind tunnel where we have, this is in a wind tunnel at Calspan in Buffalo, New York, and this is a condition of Mach 3.5, and what we're doing is we're liberating a piece of foam to try to understand its initial release aerodynamics. And you can see as it comes off, it's immediately orienting in aerodynamic trim, and that tells us it's in a very high drag configuration, and that drag is really critical to the understanding of where the debris goes and how fast it can hit. We have one other video.
That's all video.
Okay, that's all the video. Okay, and then the last chart I wanted to show you is we've also been firing small divots down a ballistic range. This is a little hard to see. This is actually one of the divots we fired. It's a plastic model of a divot. It's scaled for mass so that it represents the conditions as if that was a full-scale divot flying. And what that picture represented was a divot being fired at Mach 2 in a ballistic range at the Ames Research Center. And what you can see is that the divot is remarkably stable. It really was quite surprising to us. Initially, we imagined that all the foam would tumble. And what we found was with divots that come off the tank, they actually trim up aerodynamically so that the small face, if you imagine it's a dish, the small face is facing into the wind, and it trims up, and that causes the drag to go up quite a bit. And that changed our computations quite a bit. So that's pretty much what I wanted to talk to you today about, how debris is a threat to us, about how we model where debris goes so that we can understand how to manage it, and then how we've attempted to validate the models that we're using to develop our management strategies. That's it.
Sandy?
Good morning. Justin Kerr. I'm the test director for the Shuttle Impact Test Program. This morning I wanted to talk to you a little bit about the test and analysis program that this great team across the agency has undertaken over the past couple of years. Like I said, we have a number of folks, some of the best and brightest across the agency that have been working on this impact problem. A couple of recommendations stem from the Columbia Accident Investigation Board. They made a couple of recommendations. One was to develop physics-based models and to, through tests, better understand the thermal protection system's capability to withstand impact. Keep in mind that the thermal protection system was designed to withstand thermal loads at re-entry. It wasn't necessarily designed to withstand impacts by ascent debris. That being said, there is an intrinsic capability of those materials to withstand impact, and it was those thresholds of damage that we were trying to establish through our test and analysis techniques. We use an iterative sort of approach. Using the scientific method, we posed a hypothesis. We made our best guess at our best educated guess at how the materials would respond to an impact. These preliminary guesses were used to develop our test plans. Those test plans were then executed at a number of test sites. We had 8 test facilities across the agency. All of those facilities use best practices and common techniques that were developed over the past number of months during the STS-114 investigation. Therefore, the entire team was using the same sort of approach in test and analysis. What's interesting about the iterative approach that we use is that our best estimates were made, our test plans were executed, and then we use the results of those tests to improve our modeling techniques. So that circle, that iteration, is what has resulted in improved understanding of the thermal protection system with respect to impact. Keep in mind that impacts on thermal protection system have a tendency to degrade the capability of the system to withstand that thermal load. There's a second step in the process. The impact portion is the part that I'm going to be talking about today. There's a second part of this work that establishes, given a damage to the TPS, how does the TPS have the capacity to withstand the heating loads in particular locations? Different materials respond in different ways. So the leading edge has a damage threshold which is very different from, say, the windows or the TPS tile material. And it's through a total of over 2,500 tests that we've conducted in this test program that we've evaluated these thresholds for each of these materials. We've impacted foam materials, ice, and ablator type materials on the various elements of the shuttle system. The orbiter conducted over 1,700 tests on tile, windows, and reinforced carbon leading edge material. SRB conducted over 500 tests on their system. The SSME, about 74 tests, and the external tank, approximately 200 tests. With that, I want to move on to show you what we call our home movies. These are high-speed videos that show the results of some of our tests, characteristic of some of our tests that we've conducted. I'll start out by showing the Southwest Research Institute. There's a large gun that we use there. It's an outdoor range. We use this compressed gas gun to launch these simulated pieces of debris at targets. And we'll start the first movie. This shows the large compressed gas gun outside at Southwest Research. In the background, you see an RCC panel. That's the gray curved structure there. A lot of folks that it takes to set up a test and all of the instrumentation, like measuring strains and accelerations, also measuring everything with high-speed video so we can reconstruct exactly what happened post-test. This shows a technician loading a piece of simulated debris, a piece of foam, into the barrel of the gun. The gun is buttoned up, and a pressure chamber is pulled towards the barrel there. We use a compressed gas to actually fire the foam at the target. What you're going to see in a moment is a foam impact at full speed. And watch carefully. You won't be able to see the foam impact the target unless you have very good eyes. That was it. It's very fast. What I'm going to show you next are high-speed videos. That was captured at a framing rate of about 32 frames a second. The videos I'll be showing you now were captured at framing rates of about 20,000 frames per second. So it'll look to you like the foam is moving or the debris is moving very slowly, but I can assure you it's moving at upwards of 1,000 feet per second. The next video, please. I'm going to show you some impacts on tile first. Then we'll move into some impacts on RCC with various debris types. The first set of impacts I want to show you, the target is an aged thermal protection system tile array. It'll be impacted by a 1 by 1 by 1.6 piece of foam. And if I can just show you real quickly to give you an idea of scale, this is what a 1 by 1 by 1.6 piece of foam looks like. It's about 0.002 pounds or 1 gram of mass. It's very light. This is typical of the sort of if you hear the term popcorning on the external tank. This is about the size of popcorn that comes off of the external tank, potentially. We're going to impact this target at an impact angle of about 10 degrees, which 10 degrees and less is probably more typical of the sort of impacts that could occur on the vehicle, and with an impact velocity of around almost 1,900 feet per second. So roll the video. A side view of the impact. This will roll a couple of times. The foam leaves the barrel of the gun. You see on the left-hand side, this is a target, tile target. You see some material coming up off the surface there. The foam strikes the target and some coating is removed from the surface. I'm going to show you another angle where you're looking kind of down the barrel of the gun. And what you'll see is the foam compress and strike. The coating peels up off of the tile and propagates downrange. This sort of damage is what's considered would be more typical of the sort of damages that we've seen in our flight history. So roll one more time. The black material is the glass coating. The white material is the tile substrate. You'll hear me use that term a couple of times. In the next series of videos, what you'll see is a new tile, TPS tile array. We'll be striking it with a bit larger piece of foam. It's a 0.04 pound mass of foam. We'll be impacting at an angle of about 30 degrees and an impact velocity of around almost 800 feet per second. And if I can show this piece of foam again, just to show the scale, this is the 002 pound foam, 1 gram, and this is the 0.04 pound foam. This large piece is more representative of the sort of max allowable, not that we would expect it, but the sort of max allowable that could be shed from the external tank. And if we can roll the first video. This shows a side view again. This projectile compresses, strikes the tile target. This is at a much higher impact angle, larger mass, lower velocity. All of these variables contribute to whether the tile target fails or has a greater or lesser extent of damage. We'll show you another shot, another angle looking down the barrel of the gun here. You'll see a little better in this angle. The foam strikes, compresses. There's quite a bit of compression initially before you even break the tile material. It takes a bit of time for the foam to load up to increase density and actually load up to fail the part. And what you see in this case is primarily coating damage or the loss of the black material. There's a bit of substrate that's lost as well. I believe there's about a 1/4 inch of depth of crater on this test. And depending on where this damage occurred on the orbiter, it may or may not be critical. There are certainly, during reentry, certain areas of the belly of the orbiter are heated to greater degrees than others. And so depending on the location of one of these hits, you can tolerate more or less damage. Keep in mind again, I tried to remind you earlier that these are all captured at 20,000 frames per second. This event is happening in the blink of an eye. It's easy if you haven't seen these before to lose track of that. In the next video, we'll see a test using a new material called Tyvek that we're using to cover our forward reaction control system thrusters. These thrusters are located near the nose, in the nose of the orbiter. There was a concern that butcher paper material that was being used for those forward reaction control thrusters had the potential to damage windows and damage tiles around the windows. Some testing was conducted with the butcher paper, and this Tyvek cover was recommended as a design change. The cover is designed to release from the orbiter nearly just after it lifts off from the pad. These things should peel off and fall to the ground. And what we were demonstrating in these impact tests is that even if the Tyvek cover strikes RCC or tile, it will not damage those structures. Let's go to the video, please. This video will show what's representative of an ohms pod tile material. That's the Tyvek cover. It's striking the tile panel. It stagnates against the panel, and you see that there's no damage to the tile after the impact. We conducted very similar tests on RCC material and likewise had no damage up to the RCC leading edge. So we believe through this testing we've verified that the redesign of those covers is a successful redesign. The next video, what we're showing here is a simulation using what's called the LS-DYNA tool. This is a computer code that we use to simulate impacts of foam and debris on RCC structures. The tile test program used primarily an empirical approach. That is, we conducted many impact tests on tile material and essentially covering the entire expected or possible range of impact velocities and angles, and produced a series of curve fits that described exactly how the tile would respond when impacted. With RCC, we had very few RCC resources. We didn't have much material to work with. We had to be smarter about exactly how we used the RCC in test. And so most of our thresholds are actually based on analysis and verified by limited testing. Some small-scale coupon testing and even more limited full-scale panel testing. This shows the impact of a 0.03 pound mass of foam at an impact angle of 45 degrees and about 1,700 feet per second. We show the video. It's a finite element code, finite element model. It shows the foam strike the apex. You notice the deflection of the apex during the impact. The yellow L shape there is actually showing that the model predicts a true failure at the panel at that location under these simulation conditions. What I'll be showing you next are videos of some actual tests that we've conducted with RCC. If you'll step to the next video. I'm going to show you a past condition, a condition where we didn't damage the target, and then I'm going to show you a condition where we did damage the target. And the reason we're showing you this is so you can see that we've demonstrated the thresholds, the threshold of failure for the RCC material through testing. You have to have a pass and you have to have a fail condition to establish where the line in the sand is. And so in this case, we had this 0.04 pound mass, the large piece of foam that I showed you earlier, striking at about 1420 feet per second at a 45-degree impact angle. So you'll start the video. I'll show three angles. This is kind of a full view. You see the panels, the foam strike the apex of the panel. A close-up view shows the foam very nearly compressed down to a flat piece of foam. You can hardly see it when it impacts. And then it moves off the surface without any damage to the target. The next test I'm going to show you is a fail condition of the same panel. You'll roll the next video. This shows a wide angle first, same piece of foam, a little higher velocity, and it strikes the panel. You see this line form on the panel itself and a bit of debris come off the surface. So it's actually a failure of the coating. It's not a through crack of the panel. It's actually a coating loss. And depending on where that crack formed and on which panel, that sort of coating loss could be critical damage on the orbiter, depending on where that coating was lost. Note again the deflection of the panel. You see the coating released. You also see the great compression of the foam. One more angle that shows the deflection a little better. It's about an 8-inch long coating loss in the RCC panel. You see some other skid marks on that panel. We use these resources over and over again to try to establish damage thresholds. We had very few panels available that weren't being used to fly shuttles, and so we used them to the greatest extent we could without invalidating our test results. The next set of videos I want to show you are ice impacts on RCC, and ice is a little different animal than foam. There's the potential that ice can form on the external tank and be released, and if it's released early enough in our trajectory, it has the potential to cause damage to the leading edge. Again, we perform these tests to try to establish the thresholds. They don't necessarily indicate a likelihood of occurrence. The first test will show a 7/8 inch diameter by 1 5/16 inch long cylinder. If I can show you real quickly, this is about the size of ice that we're talking about. It's about a 0.026 pound mass of ice that we launched at the target. So we can roll the video. The first condition, you see the ice shatter into a number of pieces. There's a bit of deflection of the panel, and the ice moves off the panel without any damage. One more time. In the next video, I'm going to show you the same piece of ice, a little faster velocity, and damage to the panel. In this case, higher velocity, and we did produce a hole in the panel. We established the threshold for this RCC material. The white material that you see moving into the field now is actually an artifact of the test itself, what's called sabot, or foam. Sabots that we use to carry the projectile to the target is made up of foam material. With our high-speed cameras, we're able to verify that that's not causing any other damage to the target. It's just an artifact of the test. With that, hope you enjoyed the home movies, some examples of the sort of testing that we've been doing. It's been an exhaustive effort by a great team of folks I've been happy to work with. And with that, I'll pass it over.
Well, good morning. These are really exciting days in the life of NASA, and I'm sure that you share that by just your presence here today. We spent the last 2 years at the Machine Assembly Facility in Marshall Space Flight Center and all over NASA trying to understand the characteristics of foam and why foam sheds, to understand the root cause of foam loss. We have performed hundreds of tests and completed analysis on those tests. And through the test and analysis, we are confident in the design of ET-120 that we delivered on New Year's Eve. We believe that this tank is the safest that NASA has ever flown, and we're excited about flying. I have an animated video that I want to show you to step through the changes that we have made to ET-120. So if I could have the video, please. First of all, the external tank is composed of 3 major components: the hydrogen tank, the inner tank, and the oxygen tank. Within the inner tank, there's a cross-beam structure that you're going to see coming up that provides the structure to attach the SRBs and then the forward dome. And then it's going to key in on the changes that we've made. The bipod fitting, first you're going to see the original bipod that had the foam ramp, and then you'll see the new design coming up. The bipod, the purpose of the bipod is to attach the external tank, the orbiter to the external tank in the forward attach point. The flange, inner tank to hydrogen flange, is attached by bolts. And I'll talk about this, the design as we come back. The lock feed line bellows, there are 5 bellows along the 70-foot feed line, and the purpose of those is to allow the feed line to move. The protuberance air load, the power ramp, protects the cable trays and feed lines from airflow and flutter. And then the camera that is installed in the feed line fairing, as you can see. Okay, the next video is just going to key in on the changes. Well, NDE, we also have performed non-destructive evaluation, terahertz and backscatter on the POW ramps to ensure that we did not have voids in those POW ramps that would exceed the allowable. Okay, if I can have the next chart, please. Okay, the bipod, originally there was a foam ramp over the bipod to protect ice from forming and also aerodynamic heating. Next chart, please. This is the new design. We've eliminated the foam ramp. We've added 4 rod heaters. They're 1/2 inch by 5 inches, and this is to protect from ice from forming on the bipod. And we've also added an Inconel 718 end cover to protect against aerodynamic heating. Okay, next chart. The inner tank to hydrogen tank flange, we reversed the bolts, and now the longer part of the bolt is in the stringer so that we can get a closeout and to prevent voids in that area. We also applied Loctite to the threads to restrict the liquid nitrogen from seeping into those areas. And then we now have a 3-step manual closeout where we can control the process to ensure that we do not get voids as we spray the foam. The lock feed line bellows, again, there are 5 bellows 3 of the bellows are exposed. The other 2 are inside the inner tank. The purpose of these is to allow movement during tanking and also during ascent. We have added a drip lip to this to reshape the edge so that the condensate drips off rather than forming around that bellows area, which could be a debris source. And then the camera is mounted in the liquid oxygen feedline fairing. It's a 3.5 millimeter lens camera, and it provides a field of view of about 100 degrees. We can see the bipod attached fitting, also the flange area and the bottom side of the orbiter. The other thing that I want to talk about is just the process that we have added to for applying the foam. Prior to Columbia, we just did not understand foam, how the foam loss, and we were not that sensitive to spraying the foam. When we apply foam at this point, we assure that all of the parameters are within the realms that we have identified. We make sure that the overlap times are appropriate. We make sure that the temperature is appropriate. We have 2 expert video sprayers that are one watching, the other spraying. We film the video to make sure that voids are not being formed as we're spraying the foam. So we're taking extreme caution in all of our sprays to assure that voids are not forming. I guess the critical thing in understanding foam loss was we found that voids are the main reason for foam loss, and by taking extra precaution in spraying, now we have assured ourselves that we have a good foam spray in all of the redesigns that we have accomplished. Okay, with this we have additional video, I believe. Okay, this is the processing in the machine assembly facility of ET-120, and this was that glorious day when we rolled ET-120 out. Beautiful, beautiful morning. I tell you, it was the highlight of my career and of all of us at the machine assembly facility. It was a beautiful morning, and when those doors opened, it was just like birthing a baby. And I guess as we prepare her now to move out to the pad, it's almost like she's gone through her PhD and she's ready to accomplish the world. This was leaving the machine assembly facility. Exciting times. And with that, I guess that completes my...
We'll let Justin go ahead now.
Thank you, Justin. You guys have certainly done a great deal of testing, and hats off to your team, John and Sandy, you guys as well. And the SRB project, over the last couple of years, we've made a great deal of progress as well. We're very excited about STS-114 rolling to the pad and getting ready for return to flight. But several months ago, we first started moving STS-114 SRB hardware over to the VAB, and that stacking operation is gone very well. We're actually beginning the stacking of STS-121. The hardware for STS-115 and subsequents are in various manufacturing phases in the manufacturing facility down at Kennedy Space Center. The SRB project USA, the folks at KSC, and as well as at Marshall have done a great job in getting us ready for return to flight, and we're very anxious for that to occur. Relative to debris mitigation, we've made several changes in the SRB. We've redesigned the bolt catcher, and I'll talk about that in a little more detail in a few moments, but we've also done a good deal of camera work. And we've done a great deal, as Justin mentioned, of debris impact and tolerance testing to understand the SRB's thresholds relative to impacts from foam and ice and thermal protection materials. If you'll pull up the first still, I'd like to go ahead and start orienting you to where the bolt catcher is on the vehicle. It's within the red circle. is the forward attach point between the SRBs and the external tank. That's actually the thrust post on the SRBs that transfers all of the thrust, forward thrust from the SRBs into the external tank and subsequently into the orbiter itself. And the bulk catcher is a high-tech term for a catcher's mitt, if you will. It actually describes its function. At T+2 minutes, when it's time to separate the boosters from the vehicle, there's a large bolt in that attach point that fractures after a pyrotechnic event and allows the vehicle to move away. And the forward portion of that bolt is captured within the bulk catcher, and the bottom portion of that bolt is dropped into the thrust post. Next slide, please. Here's a close-up view of the bulk catcher. On the left, you can see the SRB. On the right is the external tank. The bulk catcher is actually fastened to the external tank at the thrust beam that Sandy mentioned earlier. It actually it stays with the external tank after separation and travels with the vehicle. The lower portion of the bulk that drops into the thrust post, and you can see the separation plane there as depicted by the red dotted line, is dropped into the thrust post, and we get the boosters back, as most of you know, and we get a look at that hardware. Next slide, please. This is a photograph of the actual STS-114 bulk catcher being installed by one of our very conscientious technicians that we have in the VAB. They're all over the program. We've got them in the ARF. They're the assembly and refurbishment facility for the booster. This is Todd Reeves. It's not every day that you actually see a mechanic or a technician wielding a wrench with rubber gloves. But that's just indicative of the care and the diligence that these guys that actually build the hardware, the guys that actually lay hands on the hardware, they take a lot of pride. We spend a lot of time with these guys on the floor watching their processes, and we learn as much from them as we do from our engineering community. They're a wealth of knowledge, and they've actually done a bang-up job. They're super guys. Todd's just one example, but our hat's off to the team of technicians that have done a great job of getting the STS-114 stack ready to go. So we're very proud of those guys, and they've done a great job. Next slide is actually a cutaway graphic that shows some of the inner workings of the separation bolt. The bolt catcher, as I said, is attached to the external tank. The separation plane you can see between the yellow and blue depicts the difference between the external tank, solid rocket booster. The separation bolt, the bolt half on the top that actually gets captured in the bolt catcher weighs about 31 pounds, and when it's traveling into the bolt catcher, it's traveling at about 65 miles an hour. So it's a pretty exciting event, and it's a very critical element that has to work every time with excessive margin to make sure that we don't have a serious debris event in our hands. So we've done a great deal of testing to make sure that this new bolt catcher is doing its intended purpose. And with that, I'm going to move over to the show and tell and talk to you a little bit about the specifics of the bolt catcher redesign and some of the changes that we've actually made. This is the old bolt catcher, and this is the new bolt catcher. This is actually the portion of the bolt that gets captured into the bolt catcher. It's essentially an aluminum canister made out of aluminum alloy, and on the interior surface is a honeycomb material that acts as an energy absorber. And on the external portion of the bolt catcher, we have a thermal protection system for the new bolt catcher. It's a cork material. But relative to some of the specific changes that we've made, they're both aluminum alloys, but this bolt catcher is aluminum alloy with a little bit more strength. It's about 12% stronger than the old bolt catcher from a material standpoint alone. We've also increased the thickness of the bolt catcher from 1/8 of an inch to 1/4 of an inch. So we've doubled the thickness of the bolt catcher itself. But probably the most significant structural improvement that we've made to the element is the old design, if you can see, has a weld. It's a two-piece manufacturing process, and in our early testing, we realized that weld was actually the weak point in the structure. So we've eliminated the weld by machining the bolt catcher out of a one piece of aluminum and eliminating that failure mode. So we've increased the thickness, increased the material strength, eliminated the weld. We've also increased the size of the fasteners that are used to attach the bolt catcher to the external tank. We've gone from a 3/8 inch diameter bolt to a 9/16 inch diameter bolt. So we've really done a significant amount of improvements relative to the structural capability of the bolt catcher itself. Relative to the forces that are imparted on the bolt catcher, we've done some work regarding the honeycomb material. It's an aluminum honeycomb material. We actually decreased the density of the foam in the new bolt catcher. We've gone from a 1400 psi crush strength material down to about an 800 psi crush strength material. And what that allows us to do from a physics standpoint is it extends the length of time by which we decelerate this bolt half. It extends the distance by a short amount. It decelerates over a longer period of time, and so what that does, it decreases the forces that the bolt catcher structure has to withstand. So we sort of attacked both sides of the equation relative to the bolt catcher. We've significantly increased the capability, but we've also decreased the forces that the bolt catcher has to withstand. So this is an item that was cited in the CABE report as an area that the Solid Rocket Booster project had to address, and we've done that. It's passed a significant amount of testing with flying colors. This is actually an item that we do have closed out with the Stafford Covey team, and the team's done a great job in improving the bolt catcher and getting it ready for flight. With that, I'd like to go through to a couple videos. There are a couple gee whiz videos that show the separation event from some various angles, and it'll also give you an idea of some of the imagery that you'll see on 114, some of the camera work that you can expect to see on 114 and on subsequent flights. So if you roll the first video, the first video is a view from the orbiter umbilical well. It's at the aft attach point where we have 3 struts. At the aft portion of the booster, there are 3 struts that have a pyrotechnic explosive bolt arrangement very similar to the bolt catcher where we have honeycomb. We've done a great deal of testing to understand the separation loads in that area as well. Where those struts attached to the booster is an ET attach ring, and there as well we've done a great deal of material characterization testing to make sure that we have all the confidence that we need in the safety factors for the ETA ring on STS-114. Next video, please, shows an event from the forward attach point. This is a camera we'll have on STS-114. It actually shows the booster separation motors. You can see the Earth's horizon in the back, but this is a view from the right-hand booster looking over the external tank and at the left-hand booster. It's a camera. It's very useful for us to see the separation event as well as see the TPS performance in the intertank region of the external tank. So those 2 cameras in conjunction with the ET camera that Sandy mentioned, and Christine's going to talk in more detail this afternoon about the imagery. But that's a taste of what we'll see on STS-114. On STS-115 and subsequent flights, we'll have some additional cameras on the solid rocket booster, one on the forward skirt looking aft, one on the ET attach ring looking forward. And that's really all I had relative to the SRB changes from a debris mitigation standpoint. There's been a great deal of effort and time, and the teams have really stepped up to the plate, and I wanted to say hats off to all the SRB team members and their families for the dedication with our objective, and our objective all along and will continue to be is to put the best SRB out on the launch pad that we can possibly manufacture. We've done that for 114, we'll do that for 121, we're doing that for the subsequents, and that's always our goal. Thanks for your time.
Wait for the mic. John, up here in the front row, go ahead and get Seth since he's close.
Seth Ornstein, night reader. I guess either for Dr. Kerr or for Mr. Murator, you've gone through all the testing data, so the bottom line is, where is the point with ice and foam, and at what point do you get the critical hits that are just too much to go? I mean, because I guess, Dr. Kerr, you talked about at faster velocity for the ice, it failed. You didn't tell us what faster velocity that was. So I'm just wondering, where is that critical point for both the foam and the ice?
It's not one answer. It's from where depends. So I'm not trying to be evasive about the point, but sort of the minimum foam size that we believe would be a problem in flight is on the order of 0.02 pounds, okay? But it depends on your assumptions about how it comes off and what the characteristics of the material are. When we started this activity, we thought there was a very crisp definition of we thought that we could have a very crisp definition about what the impact tolerance for everything was and what the damage environment would be, okay? And we thought we were going to be able to show margin there. And it all depends on the conditions. And what we found is that because we have a small number of test articles, when we have a small number of tests, there's sort of a cloud of uncertainty around each estimate, and there's some overlap between those two estimates. And we don't have the physical assets to keep testing until we could really define that uncertainty away. And the fact that we're doing it on the ground at sea level, not at flying at the speeds we are, at the temperatures we are, and in the density we are, really limits our ability to go compute that. So what we did was, what we've done is made our best estimates of what the impact tolerance is and what the debris size and the debris impacts are like, and we've convinced ourselves that we've got a margin between those two that there's a reasonable risk to go fly.
Yeah, I guess just to follow up is right on that. If you still have this cloud of uncertainty and the margin, how close are you? I mean, I guess when you have a cloud of uncertainty, doesn't that just translate into the risk to go flying? So how close are you on the edge of the cloud of uncertainty, when it comes to the staff recovery team and the mission management team to decide, are you just at the edge of that cloud, or I mean, are you? I guess I'm just trying to understand how, if you've got a cloud of uncertainty, how can you be fairly confident that it's okay?
This is a very difficult engineering problem, and it has characteristics similar to other engineering problems that we deal with. And what we do is we try to express the conditions that we do the analysis on. And we express for example, on the materials, the impact, how strong is, you ask the question, how strong is an RCC panel? Well, the answer is it depends. How old is the RCC panel? How many flights has it been through? The manufacturing of the panel, there is a normal variation in the material strength and in the manufacturing thickness. And it varies whether you're on a panel at panel 8 or panel 22, the strength varies because of that. So we try to put all of those factors and try to put it together in an end-to-end model. And when we make our best estimates of those, we believe the best estimate shows that the risk is low to go fly, that there is margin between our best estimate of what we think the impact conditions will be and what the impact tolerance is.
Yeah, Horst Rademacher, Frankfurter Allgemeine Zeitung, Germany. I have a question for Dr. Kerr. You showed some of the impacts with beautifully shaped cubes and cylinders and, nicely shaped forms of foam or ice. But of course, if something comes off the tank, it will not be as beautiful as you showed it. It will have some arbitrary shape. Does that make a difference in your testing? If you get an icicle come off the ET, would that cause more damage than one of your nice cylinders that you showed?
Well, certainly the sort of sizes and shapes that we used we consider like a bounding box or a bounding case. We utilized these rectangular prisms or circular cylinders as a representation of the debris that's coming off the vehicle. We have performed analytical sensitivities where we had shaped divot-shaped foam that we impacted against tile and we've impacted against RCC, and we've looked at those sort of sensitivities. And in general, the bounding shapes that we're using provide a conservative answer to the problem. Certainly the results would be different, but the sort of approach that we're taking through testing is characteristic and would be conservative if the divot were to fit inside of that bounding box.
Los Angeles Times. Does the redesign of the foam, the bipod foam ramp, mean that debris won't come off that ramp in the future, or that if debris does come off that ramp, it won't hit the impact the orbiter?
Well, the foam ramp has been removed, and so there's still a closeout there, but we are confident that the new process we will not exceed the debris allowable.
To give you kind of a scale, the foam ramp was about 1.8 pounds. The allowable that we set on the tank in this region was about 0.03 pounds, and what their actual measurements, our best estimate is that it'll probably be 0.002 or 3 pounds coming off that. So, we're moving across 4 or 5 orders of magnitude in terms of difference.
Mark Kirkman, Interspace News. This is for Mr. Meritor, I guess. I understand that imagery is going to be much better, but given a degree event like we had on 107, you get footage that there's something falling from the tank. Take me through how you're brought into the process of reviewing it, and how quickly or how realistically quickly can you come up with an estimate of the impact energy of this debris and give that to the program. And I also have a follow-up too.
Okay, well, we ran through that very scenario in a simulation last month, and it depends on which assets are involved. I think it's safe to say that our whole aerodynamics team is locked and loaded. We're all going to be ready, because with a tremendous amount of imagery we've put in place and with all the radar measurements we've put in place in addition to imagery, we're expecting to see more debris than we've ever seen before. That doesn't mean that there's more in the environment. In fact, we believe there's going to be a significantly reduced debris environment. But our ability to detect it has improved so dramatically that we're expecting to have to go process through all of that data. So we'll be set and ready to go at liftoff. Matter of fact, we'll be on console before liftoff to evaluate any ice formations that might occur on the tank. And we'll be set to go, and we've got a plan in place, and we've practiced that plan by within 24 hours we have a first cut at what the velocity and impact conditions are, and within 48 hours we've pretty much refined it to a pretty definite state. Now, that assumes we have enough observation data in order to go do that. You know, if you capture, in one frame of the video, you capture there's some debris flying near the vehicle, but that's all we see, we're not going to be able to do anything with that. If the radar tracks it coming off the vehicle, if the photography shows the location of impact, well, then that'll give us the parameters to go do the estimate. Even if we don't have a really solid track on its entire trajectory, we've done enough of the trajectory so we can sort of put it in a box.
And this is, I guess, kind of an aerodynamics question alluding to what you were talking about earlier. Given that the velocity is increasing during first stage ascent and the density is decreasing, is there a point in the trajectory where a given object comes off that has more energy than, say, it that liberates earlier versus later, and when is that?
Yeah, the maximum for the impact energy, it depends on the exact material, but it's around Mach 2.75, okay? It's a little higher for ice than it is for foam, but it's all around that region. About 100 seconds in flight, somewhere around there.
Bill Harwood, CBS. A question for Justin, the same question for John Meritor. Just to follow up on these earlier questions, you have a certain amount of foam you expect to come off the tank based on how the foam's been applied now that you understand it. And I realize you guys have meetings coming up where you're going to put numbers on this, but in general terms, the maximum stuff that you expect to come off the tank, can it or can it not, in worst case scenarios, cause RCC damage for Justin? And for John, same question for Tile. I mean, you've obviously said you're going to have to accept some risk to fly. I assume by that you mean if a piece comes off the tank that is within the realm that Sandy tells you could come off the tank, can that, in worst case scenarios, cause intracritical damage? I mean, that's a up or down kind of question. I realize you don't have numbers yet, but can it?
There's 155 things that we look at in terms of debris. And so in terms of the foam, we have our best estimates of what the foam debris loss is going to be. And with our best estimates of the foam debris loss and our best estimates of the RCC impact tolerance, we don't believe that expected foam can cause any damage to RCC. With regard to ice on RCC, depending on where the ice comes off of and how big it is, it can cause damage. And we've put in launch commit criteria to try to steer us away from any region where we believe we could create critical damage. In terms of tile, it's very hard to protect any damage from tile. So the question is how do you know that you can prevent any damage that would prevent the orbiter from returning safe? And I think in terms of that, the sizes that we are expecting to be liberated from the tank in a worst case condition can cause significant damage. It all depends on the location and the depth that it actually occurs and the underlying structure. That is significantly outside of our flight experience. So the question comes in is the cloud of uncertainty about the damage response of the vehicle and the transport mechanism very conservative. And we're struggling with that problem right now. It's a very difficult engineering problem. So there is some risk we're accepting that if the conditions are different than our best estimates, that we could take serious damage, and that's the risk that we're going to have to take.
Is there anything that, just for the record, obviously, I mean, if you spent 10 more years working on this, you could do something, but I mean, the design of the vehicle is what it is. And so my question is, there must be some line where you have to draw a line and say, okay, I can spend more time and money trying to fix this, or you accept the risk and go fly. You guys are obviously at the point of the latter, but can you talk about that a little bit about, you know, what additional time might buy you in this regard, or is this something that there's simply nothing at this point you can do about, and you either accept it or you don't fly?
I think that we feel that the main way we can get smarter about this problem is go fly. We have come to the point, as it comes in every experimental vehicle, where the amount of analysis and modeling and ground test has sort of saturated the problem, and now the only way to really know what's going to happen in the real world is to go actually perform a flight test. And you perform a flight test carefully with careful limits with careful safety devices, and that's the way this flight is constructed.
Mike Cabbage with the Orlando Sentinel for John and Sandy. And my question is essentially similar to Bill's. As far as the critical areas of the tank are concerned where you see foam shed, Have you taken the design as far as you can go without doing some major redesign of the tank, or are there things that you can do to wring out a little additional margin? As Bill just said, I mean, is what it is, or can you go further?
Well, I think the thing that we're going to be concentrating on over the next few months and years will be the non-destructive evaluation. We certainly want to perfect that so that we can make sure that we don't have voids in the foam that would create debris that's not acceptable. On third flight, we're going to add heaters to the bellows that can continue to reduce the ice around the bellows area. We've reduced it probably 40 to 60% on this flight. And those are the main two areas, but other than a major redesign, we believe that we've perfected. And I guess as we produce additional tanks, we will apply the new process to the new tanks, and that will help us to ensure that we do not have voids in the foam, in those the hand layups.
And also, what are you doing for future tanks? I know that there is work underway right now to look at additional improvements beyond the 2 tanks that have already been shipped. What are the areas that you're looking at continuing to upgrade and modify? What's the status of the PAL ramps? What are you looking at?
Well, for now, we're going to continue flying the PAL ramps on the vehicle. We've got testing underway to see if we can remove the PAL ramps. But you know, there's always risk when you make a change, and so for now we have not had PAL ramp loss. We have done NDE on the first 3 tanks, and the process that we had prior to Columbia was good. I mean, we have not found voids in the PAL ramps that would create a problem. So for now, the tank is pretty much what we're going to fly out for the program, other than perfecting the NDE and potentially putting heaters in the bellows, and again the refined process. And as we build additional tanks, we will make sure that the hand layups are good and that we don't have voids in there. We use the new process control for all of the 300 closeouts, hand closeouts that we have.
Tracy Watson with USA Today, I think for Mr. Murator. The last time the Stafford Covey Group put out a report, they expressed concerns about the analysis and the reliance on modeling. And I'm wondering if you can tell us what you've done to address those concerns, and whether you've gotten any feedback from them that the steps you've taken really address what they were worried about.
We've had discussions. We've certainly listened to the report, the interim report, and we've addressed it in a couple of different ways. One of which is we've tried to give greater exposure to the validation work that we've done to try to show that we believe that there's a good basis for the models. Another area is we've been a lot more careful about how we describe the results of the models. So we've been careful to describe the uncertainties that are associated with those. Okay, and we've also tried to communicate that the only way to performing an engineering assessment of this is to use modeling techniques. We can't go out, and we'd love to go out and fly the shuttle every day and take it to each of the test points conservatively with appropriate procedures and build up to where we have a good understanding of the performance of the vehicle in this environment. But this particular vehicle doesn't lend itself to that. So given that that's the case, this problem, like everything we do, whether it's the structural loads on the vehicle and the metal, whether it's the thermal heating of the vehicle, whether it's the aerodynamics and the flight controls, we make all of that work with modeling. And we validate those models as best we can on the ground. And we're used to talking about things like flight controls and structural loads as if it's a certainty because we have worked with those models for so long and there was such an extensive program ahead of it in order to validate it. There was something like 50,000 hours of wind tunnel runs done in the original definition of the shuttle program in order to understand the basic aerodynamics and structural loads and flight controls of the vehicle. So we tend to talk about our models as if they are certain, and we have a lot of experience where in flight we validated the models with in-flight data. I think that we carried over maybe a little of that confidence in talking about it, and that perhaps that was misinterpreted as saying that we did not recognize the uncertainty with regard to this. There are significant uncertainties with regard to this. This is an experimental test flight. And however, we believe that the rigor of doing the models, of putting all of the information we have together, whether it's the work that Sandy's done in understanding how foam comes off, the work that Justin's done on how foam causes impact, we putting all those information together in a model in order to make an assessment of the risk is the right thing to go do. And so I think maybe we communicated not very effectively about them, and we've been careful to communicate more about the uncertainties and about how we've attempted to validate these models.
And what kind of feedback have you gotten from them about whether your explanation satisfied them?
We're not finished with that process yet.
June Sincere, ABC News for John Murator. John, tell me about this next flight. What information you will be receiving and what you will be looking for and when you will have enough information?
Okay. It's a great question. We have a plan that's about 200 pages thick that describes every piece of imagery, every thing we're going to get from the radars, everything we're going to get from the sensors that are embedded in the wing leading edge, everything we're going to get from the cameras on the orbiter that are going to be looking at the tank as it separates, the imagery from the cameras on board the SRBs, the imagery from WB-57s that are going to be flying out, and it all has its own timeline. Each piece of data has its own timeline, which has been scripted out, and we have a series of reports at different times during the mission where we'll get a quick look in the first hour, then there's another set of data that comes in about 3 hours, another set of data that comes in 8 to 12 hours, another set of data that comes in 24. And so what happens is that all of those different assets report in at different times, and we go ahead and integrate them together to build the whole story. As I said, around 24 hours we'll have a pretty good handle on any debris tracks. At least that's the way it's gone in simulations. If the sensors work the way we anticipate, we believe we'll have a pretty good track. And then about 48 hours later we'll have refined, about 48 hours in the mission we should have refined it quite a bit further. This is an experimental test flight. We've got a whole bunch of sensors that we've never used against the shuttle. We've tried them out against expendable launches. We've tried them out in the lab. We have done radar cross-section testing on debris. We've estimated debris sizes and tried to estimate what the pixel imagery resolution of the high-def TVs will be. But in the end, all I can tell you is what we've planned for to happen, and we're just going to have to see how all that works out in real time.
Marcia Dunn, Associated Press, I think for John. Could you give me the dimensions in both inches and weight for what you expect to be the biggest piece of foam to come off the tank at any location? Do you have a maximum size estimate?
Let me tell you why I struggle with the answer to that question. It seems very straightforward, but let me explain why. As we get down to the back of the tank, the bottom of the tank, there are no limits on the foam that can come off because there's no transport mechanism to anything critical. So down near the bottom of the tank, the allowables are quite large. Up at the very tip of the tank is the place where it's the greatest hazard to us. And in that area, the allowable is 0.02 pounds, and the expected is on the order of magnitude less than that, something like 0.002 pounds. And I think just yet at 0.02 pounds, that's what? That's 0.002. That's sort of what we expect to be coming off the top of the tank. The allowable that we've analyzed is up to 10 times larger than that.
This is 0.03.
Yeah, this would be sort of what would be allowable off the bipod area size.
But I mean, not allowable, but maximum expected.
In general, the maximum expected is about an order of magnitude, a factor of 10 less.
But you can't just give me, like, I know a few months ago we got the dinner roll cupcake size. Is there any way that you could sort of just make an analogy of what you're, in the critical area, what you expect to be the biggest piece to see come off? Whether or not it can do damage is another question.
Say the critical area, it's all critical.
Oh, okay. Well, then the entire thing, I mean, the testing that we have completed just shows that we are not going to lose foam at 0.03. I mean, this is the allowable, and we are certifying to this, but we don't expect to lose, I mean, basically we don't expect to lose any, but certainly nothing that big. The testing has just shown that we're not going to lose foam. And I think in one of the interviews I said 0.01. I mean, it probably won't do that much because that's why our testing is just much less than that. But we just do not expect to lose foam. We think the design is good.
You really just can't.
But you can't guarantee that. That's the key.
Is that you just can't estimate, or it's impossible to say then?
Well, it's impossible to say exactly what you're going to lose because you don't know everything. We don't have a non-destructive evaluation that we can evaluate the whole tank. The testing and the dissections we've done have shown that we do not have voids in the foam that's going to cause a problem. And that's just the best we can do is evaluate. We've dissected, we've run tests, and with everything we've done, we don't believe that we're going to lose anything that's 0.03.
I mean, I think just in that, I think because have this focus, this is the 0.002 size, or it's a 0.002 size, 0.002 pounds. This is our best estimate of the voids, remnants in the tank that are as of the nature of processing and spraying foam onto the tank that we would expect to come off. And this does not represent a threat to the RCC. And and you saw the results of the tile test that Justin showed with that. So this is on the magnitude of the size that we would expect to see. I guess if that, I mean.
Todd Halverson of Florida Today for Sandy Coleman. Over the history of the program, there has been peaks and valleys in terms of foam loss, and I think there have been probably 10 or 11 different attempts to fix the shedding problem. I'm wondering, how can you be certain after 2 test flights that you've licked the problem for good?
Well, in the past, when we've had foam loss, we did not do the amount of testing that we have done over the past 2 years. We did not totally understand the root cause of foam loss. And over the past 2 years, we have run enough tests and done enough analysis that we believe that we have captured the root cause. And that's what gives us the confidence now that we fixed the problem.
Okay, and I don't know if this is for John or Justin, but we all know it was a 1.7 or 1.67 pound piece of debris that's down Columbia, and we also know that your testing has shown that a much smaller piece of debris can cause entry to critical damage. If you looked at the exact same scenario as Columbia, with a piece of foam coming off of that part of the tank, how small a piece would have created critical damage, given the same circumstances as you saw in Columbia?
It's a pretty big set of hypotheticals. That's kind of hard to answer off the cuff. What I can say is that I'll give you an illustration. We launched that 1.67-pound piece of foam, and we even launched a 2.5-pound piece of foam. We had an even larger briefcase that we launched at tile structure. And given the location, the landing gear door area, given the sort of STS-114 conditions, we were unable to break the tile with a much larger mass. So there was a question earlier regarding, what size causes critical damage. It is a very complicated problem. It involves mass, it involves the velocity of the impact, and it involves the impact angle, and really to a greater extent, velocity and impact angle. So so it's an awful hard question to answer because of all of the hypotheticals. It would be a dramatically smaller piece of foam because the velocity would be much larger.
In the computations we run associated with the intertank flange region, which is very, with the bipod just sits right on top of it. Again, using a set of worst on worst case conditions, a piece of foam as small as 1/10 of a pound from that area could potentially cause damage to the RCC. Was that the same damage we saw in 107? We don't know.
Okay. Just so you know, we have time for one or two more questions here. We have one here we'll take, and if anybody else has one, raise your hand.
I'm Zipper Fowler, Shuttle Magazine. This is for you, John. At this point in getting ready for return to flight, could you prioritize your top 4 risk concerns as they relate to this cloud of uncertainty? Is there like a list of your biggest risk concerns?
The factors that affect our ability to determine this?
Right.
I think the main uncertainties have to do, and Dr. Kerr may help me with this one, have to do with the material response of the structures that we're hitting, whether it's the RCC or the tile. That work just finished up in the last 2 or 3 months. We're still analyzing through all that data. Right now we have large bands of uncertainty around that. As we work through the data and understand the configuration better, the material response to the stress is probably the biggest uncertainty. And in that, age, the actual material properties, in a batch of material, whether it's tile or RCC, each individual batch of materials has different tensile strength and compressive strength and things like that. And so all of those factors, I think, those are major elements in the uncertainty. The other issue that is in our top list of things that add to uncertainty is the actual distribution of voids in the tank. It's really important to note that External Tank Project essentially dissected an entire tank. And we took ET-94, which was fully completed, off the line, and the team at MISHU dissected it a 1/4 inch, I think, a slice at a time, 1/4 inch thickness slices at a time, looking for voids. And the smallest size void, I believe they said their rejecting criteria was 0.03 inches. And in a lot of places, we didn't find any voids at all. Essentially, over the major part of the tank, we couldn't find any voids at all. So the question is to how much each tank, that one tank that we dissected, was representative of all the tanks in the fleet. And so I think those are the 2 factors that cause us the most uncertainty in the end-to-end calculations. Sandy or Justin?
I agree.
Maybe I can jump in on the impact side. Yeah, there is some variation. There's allowable variation in the material properties for tile and RCC. The evaluation of what's critical damage on tile is it's a 2-step process. There can be a crater formed or some damage caused by the impact, and then there's this assessment of whether the thermal loading given that damaged tile whether that thermal loading is acceptable during reentry. It's all very dependent on location, so therefore it's dependent on where did the foam come off of the external tank. The tile itself has an allowable variation of about 30% in compression strength. And so we actually saw that in our testing. We did enough replicates or enough tests at the same conditions to demonstrate that sort of scatter in the data. And the scatter was just demonstrating the variation in the allowable material strength. It's all part of the design of the system as a thermal protection system. The RCC is a little different in that we've established we can tolerate a much smaller sort of a damage. And so there again, you have variations in material properties, whether the panel is aged or how many flights it's been through, and the status of its coatings. But in general, I would say that the uncertainties right now are dominated by the transport and the need to go fly to see what that environment really looks like, more so than the material properties themselves.
Okay, a few last follow-up questions. Mike, and then back over here, and we'll wrap this up.
Mark Sentinel for John. As sort of a follow-up to that last answer, Wayne Hill earlier this morning talked about possibility of a golden BB hitting in a certain spot. When you look at the orbiter, what are the places you're most concerned about that golden BB hitting? Is it the area around the landing gear door? Is it the leading edge? Where are those critical areas?
Yeah, we always worry about seals. Seals are, for an engineer, they're a solution to a particular class of problem, how to be able to change the configuration and yet maintain a certain structural integrity. So around the landing gear doors, the EP umbilical doors, those are our biggest areas of concern. The other thing that really affects this impact condition is the impact angle. And I think all of our testing has shown that that's a really major factor. It's a huge factor in tile. So as a result on the orbiter, the things that we're most concerned about is where we could have the highest impact angle, and that tends to be along the leading edge, whether in the RCC or in the tile right behind it and up in the chine area. So the areas that are most susceptible or the most concerned are areas where we have the highest angle or where we have structural seals.
Horst Dornemann of Frankfurter Allgemeine Zeitung, with a question for Dr. Coleman. You have shown us today that you're very confident that no debris or very little debris will come off the tank during the next flight, because that's what your testing shows. But have you ever considered using a totally different method of insulating the tank, thermally insulating the tank, other than foam, in order to reduce that risk completely?
Well, if we started with a whole new design, it would be years before we get that design perfected. It would take a significant amount of testing and analysis to change the foam. I mean, we've looked at or we've had suggestions of putting fibers in the foam or putting a net over the foam, but those are, again, just added debris sources. And so we do have confidence in the foam design that we have. If we started with a clean tank, we probably would do something different. We probably would move the feed lines to the opposite, to the -Z, to get them out of the debris zone. And that was on the table in a phase 3 if the program were going to 2020. At this stage, we would not get those qualified prior to the fly out of our program. So we definitely have looked at other methods, but it's just not feasible with the length of the program.
Okay. Thanks very much for all your questions. We're going to break for